All right, hello everyone. Today I'm going to be talking about inspiring philosophy again. So this is a follow-up to the debate that I did with him just a few days ago. So if you haven't watched that, it might be useful, although it's not technically required, because what I'm going to be doing today is talking about some of the more of the scientific aspects of Michael from Inspiring Philosophy's claims, particularly pertaining to the digital physics argument and some of the quantum consciousness stuff that he has argued in various of his videos. Now, I have discussed some of this before in one or two streams that I've done on Nathan's channel, Digital Gnosis. Today, I want to go through some of that in a bit more detail in some parts and cover some things that I didn't cover there, but also try to be a bit more concise than I was in that long stream. So I'm hoping this won't go for too long. And one of the reasons I'm doing this is because a number of people mentioned in the debate that I did that we didn't talk too much about the science, and there were various reasons for that. One of which was because we ended up talking more about philosophical aspects, and another was because, to be honest, Michael didn't seem that interested in talking about the scientific aspects when I brought up a few specific points. He seemed to not want to defend them too strongly. So welcome anyone who's here live, but I'm recording this at a time that I know is not convenient for most people, so that's fine. This is more of me just talking anyway. So let's make a start. Again, I want this to be fairly to the point. So what I'm going to do here is I prepared a document actually for the debate, which I didn't really refer to very much. And I'm going to be sort of running through that in combination with a video that, or maybe two videos that IP has put out over the past couple of years, and which I think are sort of useful articulations of what his key argument is. So the first one we'll be looking at, it occurs to me I'll have to reshare this, is a video arguing for the emergent universe. So that's more of his, it's this one. That's more of his, what is it? Not emergent universe, holographic principle, space-time is not fundamental sort of stuff that he argues for. Which is a little bit distinct from some of the quantum consciousness stuff that he argues, although there is overlap there. So what I'm going to be doing is going through this video, but I'll skip over a few parts of it and focus on the scientific, or not necessarily the scientific claims, but the claims that IP makes on the basis of scientific theorems or experimental results and so forth. So that's the focus of this video, not so much the philosophy, just directly the science and the implications drawn from that. My overall point being that IP is generally misrepresenting the science and making implications or drawing implications from it that I don't think are valid. So let's make a start.
In the hunt to rectify quantum mechanics with relativity, physicists discovered something known as the holographic principle, a theory which suggests the entire three-dimensional universe can be seen as two-dimensional information. In other words, the whole three-dimensional universe, the particles that make up reality, would emerge from underlying information in quantum field theory.
People finally began to articulate this new principle, this holographic principle. And what it said is that all the things that were falling inside a black hole were somehow captured in a preserved image at the horizon itself.
So if the information is not lost on the surface, the information is not lost inside because they are equivalent.
All the information about those objects, what they were like in their three-dimensional existence, was preserved or encoded on the surface of the black hole. And that's a little bit like a hologram.
Well, that suggests that maybe that idea may apply more broadly to the universe as a whole. Maybe the three-dimensional objects, us, everything, the world around us, maybe all of the information in these objects is smeared around a distant two-dimensional surface that surrounds us, and we're just in some sense a holographic projection of that distant data.
The holographic principle tells us something quite astonishing. It says that our ideas of volume, of the real world in a sense, might be a kind of illusion.
The holographic principle only worked in theory at first, with no observable data to back it.
All right, let's stop there for the moment, because that was sort of the theory, and he's going to show some experimental stuff in a moment. But let's talk about the holographic principle. The first series of, I guess, like interview clips that IP used here are fine as far as I can tell. So the holographic principle was originally, I guess, developed as a way of explaining the apparent loss of information when objects fall into black holes. So information should be understood in a quantum sense. Basically, it can be thought of as a quantum level description of a system. So like a bunch of particles that could make up a macroscopic object, or could just be individual particles. I guess the nature or the description of what these particles are and how they interact can be described quantum mechanically using a wave function or similar, and that needs to be preserved for the formalism of quantum mechanics to work. The technical term there is unitarity. Basically, it means that over time you can't lose any information about the system. It's got to all go somewhere, to put it crudely. But the problem was that if matter falls into a black hole, it seems that it all just sort of disappears from the universe, and that was a violation of unitarity. Now, in order to account for this paradox, the holographic principle was part of a solution to this paradox, where it seems that instead of, I'm not going to explain it very well. I don't fully understand it myself. But the basic idea is, as they said, the information is encoded on the boundary of the black hole, and is therefore not lost. That's interesting because you have to sort of be able to then encode all of the information about the black hole on its surface rather than sort of in its volume. So that's where the holographic aspect comes in. So that part's all fine. Let's talk a bit about what a hologram is. A hologram is a device, I guess you could say, or it's a thing that can encode information about a three-dimensional image on a two-dimensional surface. Now, you can extrapolate that to high dimensions, but let's just talk about, a regular sort of 2D hologram for the moment. So, we can make holograms, right? You've probably seen them on a lot of newer currencies have holograms on them, or maybe credit cards, things like that. There used to be a bit of a fad in the 90s, I think, with the little cards and toy things with little holograms on them. Those are not, and those are things, when you look at them and you rotate them and the image changes a bit. For a fully fledged hologram, what it will be is you'll have, basically it's a diffraction grating. So it's a series of apertures in some sort of material, which when you shine light through it from the back will reproduce a particular image of an arbitrary three-dimensional scene. So you can, form a hologram of any scene, just say a room, for example. And so you encode all of the visual information about that room onto the hologram, and that's, stored in a particular way, essentially forming a diffraction grating, if you know what that is. And then basically, if you illuminate it using a correct type of light from the back, then someone standing on the other side of that will be able to basically look back into the room and see it as it originally was, as if you were just standing outside the room. And you can move to one side or the other side, and it will appear that, the room is behind you. Now, there's nothing particularly, it's a cool effect, but there's nothing really sort of mystical or strange happening here. All it is basically it's a way of reproducing the exact pattern of light waves that you would see if you were just standing outside the actual room. Now, obviously, it's not perfect, so it won't be a complete reproduction, but that's the basic idea. So a hologram, in that sense, is a physical object that allows you to store on a two-dimensional surface, at least theoretically, all of the information, the visual information of a 3D scene, or necessary to reproduce that 3D scene. Now, the idea of the holographic principle is to sort of extrapolate that and say, and talk about it as if it's any instance of encoding information about an n-dimensional surface, or an n-dimensional volume, I guess, on an n-1 dimensional surface. So, for the example in the black hole would be encode all the information about what's in the volume of the black hole on the two-dimensional surface of the black hole. Okay? Now, this idea was then taken and applied to the universe as a whole, but in a different way. So that was what the little reference at the end was, because they didn't really explain that very clearly. Now, how does this idea about information loss in black holes relate to the universe as a whole? Well, this is what I want to explain here. Let me now reshare my document. This is going to get a bit tedious, but I don't know any other way of doing this. And let's talk about the holographic principle, as in cosmology. So not black holes. I'm talking now about cosmology, and it really is quite different. It's just the only thing they share is the basic idea of, basically going one dimension down, storing all the information in 3 dimensions and 2 dimensions. Although in the cosmological case, the number of dimensions is a bit different. Now, what IP was referring to with respect to the holographic principle cosmologically, as far as I can tell, at least, I'm pretty sure this is correct, given the reference that he mentions later, is something called the ADS-CFT correspondence. I guess it's a theory or a set of ideas or something. Now, what is this? Now, this is very complicated. This is basically an application of, I guess you could call it string theory. And this is certainly not something I pretend to understand in detail. But I have done a bit of reading on this, so I have some idea of what it's referring to. So this particular passage is taken from this book, Gauge Gravity Duality, Foundations and Applications. It's quite it's a graduate level textbook, which has quite a lot of prerequisites. But this chapter here, or the first part of this chapter, is explaining this idea called ADS CFT correspondence, which is basically an application of the holographic principle. So what is it saying? Let's have a look at this diagram quickly, which is taken from a different paper, but illustrates the point. The basic idea here is the basic question that this is answering is, we want to have a quantum theory of gravity. Because currently, we've got general relativity, which explains gravity. We've got quantum field theory, which explains everything else, or at least most other things, I guess. And we want to be able to combine them together. But currently, we lack a theory that's able to do that for various technical reasons that we need to get into here. ADS CFT correspondence is an attempt to get a quantum theory of gravity, or it's at least a step on that direction, I suppose you could say. So how does it work? Well, the way it works is by applying the holographic principle in a very particular way. As you can see, this is mentioned here. The ADS CFT correspondence is an important realization, so that's an instantiation or an instance of the holographic principle, which states that in a gravitational theory, the number of degrees of freedom in a given volume scales as the surface area of that volume. So that's what we were saying with the black hole. Volume turns into, or can be encoded in terms of the surface area. So here we've got gravity in bulk. So think of that as just our three-dimensional spatial universe plus the one dimension of time, right? Well, they've actually got time on this axis here, but just think of this as in terms of our four-dimensional space-time universe. Now, describing how gravity works in that, I'm just going to call it, for simplicity, four-dimensional space-time might be very difficult. It might be too hard to get a quantum theory of gravity or to construct one in the bulk. But maybe we could work out a theory on the boundary. So think of that as like the three-dimensional boundary of the bulk, which itself is four-dimensional. So it's probably easier to visualize this in terms of a 3D sphere and then the surface of that sphere. But remember that the number of dimensions is different, but it doesn't matter for the basic point I'm trying to make here. So suppose we could come up with a theory that works on the boundary and then kind of link that back to what's actually happening in the bulk. If that could work, then that might be a way of basically shortcutting some of the hard mathematics. If we can basically translate it into boundary land, solve the equations there, and translate them back into bulk land, which is what we're actually interested in. That is the basic idea of ADS CFT correspondence. So I've just highlighted a couple of passages here to illustrate the point. This is slightly more technical, but I'll just emphasize what I'm trying to get across here. From a mathematical point of view, this means that the theories are identical. That is the theories of explaining something in the bulk and on the boundary. So this is called the duality, right? That the two theories correspond to each other. From a physical point of view, their descriptions may differ. For instance, there may be different Lagrangians for the two theories. So don't worry if you don't know what a Lagrangian is. But one important point here is ADS CFT correspondence is a mathematical correspondence of theories. A theory in the bulk and a theory on the boundary. So basically, there's this idea like a dictionary, right? Where you look up a term or an equation or an aspect of the equation, I guess, in the bulk, and you translate that to the boundary. And then you can solve stuff on the boundary and translate it back to in the bulk. So there's a one-to-one correspondence between the terms of the theories mathematically. But that doesn't necessarily mean, as it says here, that physically the theories are the same thing. It just means that mathematically they're equivalent to each other, which means, again, you can solve things in one sort of on the boundary land and then translate them back into bulk land. And the particular form of the duality here, or the correspondence, is, well, as it says here, so the ADS CFT stands for anti-de Sitter space, which is the type of space that they're modeling in the bulk, and conformal field theory, which is the type of theory that they're describing on the boundary, as it says here. Well, QFT is actually quantum field theory, but it's sort of think of that as a similar thing here. However, this is a new type of duality which relates a quantum field theory on flat space-time to a string theory. So the basic idea is we know how to describe quantum field theory on flat space-time. That's on the boundary here. We can do that. We can't solve, or we can't properly solve, a string theory in the bulk, which is maybe the true description of quantum gravity. But if we can translate one to the other, then we can translate string theory of gravity to a quantum field theory on the boundary, solve the quantum field theory on the boundary, and then translate it back into the bulk. And what's been proved is that there is a correspondence between these two theories. Implies, as it says here, ADS CFT correspondence being a duality implies the two theories are equivalent, mathematically speaking. Now, it should be pointed out that this only applies with particular assumptions. So this is a very particular model of string theory. I don't actually know if I showed which form it is here. It's mentioned later on, but I don't think I excerpted that. I think it's 5-dimensional. I think it's a 5+5 string theory. So I think it's like 5 main dimensions with like 5 curled up ones or something. Again, I don't know too much about that. So it's not literally like 3 dimensions down to 2. I'm just using that as an analogy. Again, that's the point of like the holographic principle. It's not literally like the black hole case where it's 3 dimensions down to the 2, but it's the same idea, the basic concept of going down 1 dimension and then solving it in that dimension. Let's see. So that's the basic idea of this. Now, oh yeah, I was going to say that it's important to note that, yeah, this makes an assumption about the number of like dimensions. Also, we don't live in anti-de Sitter space. We live in de Sitter space. So there's aspects of that are like this isn't a final theory of gravity. This is like a step in that direction. But it's an interesting idea that's attracted a lot of interest recently. I think that'll do for us at the moment. Now, importantly, regardless of whether this is a correct theory or not, or whether this will end up being a successful quantum theory of gravity, it doesn't mean that gravity is somehow an illusion or space-time is somehow an illusion. All it means is that you can solve for, if it's true, of course, you can solve for stuff about space-time and gravity by a quantum field theory on the boundary of that region, and then translate those results back into the gravity. It's not even clear, like ontologically, what this would mean. Like if it means that gravity is emergent from the quantum field on the boundary, or whether that's just a mathematical convenience. It's not clear exactly what the boundary even means physically. So there's a whole lot of interpretive issues there. So to say that this has any particular philosophical implications, I think is grossly premature. For a start, the theory is not fully developed even like mathematically in terms of does it apply to our universe and so on. But also, it's just not clear what any physical implications would be. It doesn't mean that gravity is not real or that it even emerges from anything particular else. It's a mathematical formalism, and that's really all it is. Okay, so that being understood, let's now, or at least vaguely understood, hopefully, let's now jump back to the video. This one. Now, what IP is now going to do is present some empirical evidence that he claims supports this idea of an emergent universe, or the holographic principle applied cosmologically. So let's see what he has to say here.
But all that changed in 2017 when a peer-reviewed study published observable evidence for the holographic principle. They tested the model against cosmological observations of the early universe and found that the holographic model is compatible with the data that is found in the cosmic microwave background radiation. From looking at irregularities in the background radiation, their team found that simple equations of quantum field theory could explain almost all the cosmological observations, is marginally a better fit than the standard model, and could potentially explain apparent anomalies. But this would mean evidence in the cosmic microwave background radiation infers three-dimensional reality is an emergent informational construct. Observable evidence infers reality as we experience is not fundamental, but emerges from the quantum realm. This piece of data only correlates to a study from later that same year, which points out
Hang on, did he actually? I might have missed this. Oh, he didn't actually show the graphs. Okay, that's why I was a bit confused. He shows this in other videos. Okay, I'll just bring this up now. So we actually mentioned, I thought he was going to show the graphs here. Maybe he does later. This was mentioned briefly in the debate, but we didn't really get to talk about it. So do I show this? Yes, here I do. Here I do. So when I questioned him about IP about this, what he said is that this study, this is a study that he's mentioning here. Well, I don't actually have the name of it here, but he shows it up elsewhere, the title of the paper. These are some figures taken from it. Now, when I asked him about this, he said, that is Michael said, these results are consistent with his philosophical views about, well, ultimately theistic idealism and so forth. But the thing is, here he's presenting this as empirical evidence for the holographic principle, or like cosmological holographic principle, which is very different from saying it's consistent with it. I mean, something being consistent with something else just means it doesn't like conflict with it or refute it, which is an extremely weak claim. So yes, this is consistent with what he says, but then, I mean, so are all sorts of other things, right? The question is, does it support what he's saying? Does it provide evidence for it, as he claims in this video, even if he didn't in the debate? So if he's walked away from that claim, then all the better. But I'm responding to what he's saying in these videos more than what he said in the debate, because as I said, he didn't say that much about it. So let's have a look at this. So what did this paper actually examine? This paper examined the power spectrum of variations in the intensity of the basically like the matter density of the very early universe as measured by the cosmic microwave background radiation. So again, very crudely and briefly, when the universe was very young and it first became transparent to visible light, there was a sort of an initial, I guess you can think of it as a burst of light, which originated when photons were able to propagate, and that burst of light has since been stretched by the expansion of the universe to be in the microwave region of the spectrum, so fairly long wavelengths, and that is visible everywhere in the sky because obviously it happened kind of everywhere in the universe, and so wherever you look, you can see it if you sort of know what the wavelength is to look at and can factor out other sources of radiation. So this is called the cosmic microwave background radiation. So it's in the microwave spectrum. It's cosmic because it's cosmological in origin, and it's background because it kind of is everywhere. Now this tells us about the structure and density of matter in the very early universe. And for a long time, for a while at least, it was thought to be uniform everywhere. At least empirically, it seemed to be uniform everywhere, like wherever you look. But cosmologists knew that couldn't be literally the case, because then there would be no ability for structure to form. Because like if the density is exactly equal everywhere, then how could you form clumps of matter that formed galaxies and stars and so forth? So they thought that there would have to be variations in the density, and with more sensitive data, that is what they found. And what they've done here in these sorts of plots is that they look at the power spectrum of the basically the wavelengths or frequencies of the variations in the density of that radiation. And so you're seeing a power spectrum there. So L is just the number that they're giving to a particular wavelength, and this is the vertical axis here relates to the amplitude. So how intense that wavelength is. So this is a way of the details aren't super important here. I'm just trying to give the picture. This graph depicts how it depicts the structure of the variations in energy and matter in the very early universe. Okay, now cosmologists use this as a way of testing different cosmological models because they make different predictions about what they should look like. Now, what this study actually did, the one that IP is citing, is it tried to fit two different models to explain this spectrum. So what were the two models? Well, one was based on, as it says here, lambda CDM, which is the standard, insofar as there is one, the standard cosmological model. This lambda stands for the cosmological constant, which is like dark energy that's pushing the universe apart, and CDM stands for cold dark matter, which is the standard model mainstream model of dark matter. Now, they used that model to make predictions about what this would look like and then compare it to what it actually looks like. And so that's what the vertical axis here represents. It's basically how well does it fit? How well does that model fit the data? And there's some sort of error bars around that. Now, there are two lambda CDM models here. Basically, the reason for that is because they mentioned that they're comparing lambda CDM, like the standard model, with holographic cosmology, I think HC stands for. So it's a model based on the ADS CFT correspondence that I mentioned before. Now, I don't fully understand how they were able to derive that, because as I understand, the ADS CFT correspondence only applies to anti-de Sitter space, but they must have I don't know how they worked around that, but they did somehow, and were able to make predictions about the angular power spectrum of CMD anisotropies based on that sort of theory. And that's what the HC stands for. Now, the problem, though, was that the lambda CDM model had one fewer parameter than the HC model. And when you're comparing models, you want to make sure they have the same number of parameters, because the more parameters you add in, the more degrees of freedom there are, and the easier it is to fit any arbitrary data set. So you should ideally, you should compare models that have the same number of parameters, or make an adjustment for that. So the CDM with running here means that they've added in an extra parameter, essentially, to make sure that it has the same number as the HC model. So although it shows both here, I think that this is the one that should be compared because it has the same number of parameters. So that's this, basically this green line along here, and the sort of error bars on either side of it. Now the HC, you can see that they're not just a straight line, they kind of go up and down. That's because there's this parameter here I forget exactly what it represents, but they weren't sure what value to set, so they just set a range. But I mean, it doesn't vary massively. So we'll just sort of look over the whole range and see what the fit is. What we're looking for here is a difference between this green line here and either this blue one or this red one here, depending on which value you choose for one of the prior parameters of the HC here. Now, I've probably already gone into more detail than is needed, but whether they're using large beta or small beta range, that's just a parameter that is stuck into this model here, which is based on empirical data, but they don't know what the value should be, right? So there's sort of two distributions of that. Personally, I think that I think that the small beta range is more appropriate because that uses 2 sigma, which is 2 standard deviations, whereas the red here just uses the 1, which is a pretty wide range of confidence. I think it makes more sense to use 2 sigma, which is sort of more standard. But it's no definitive answer there. You can kind of argue it either way. So anyway, we can just look at either of the red or the blue as a measure of how good the holographic cosmology fits. And then this green here, I think, is the one we should look at for how well the standard model fits. And the point that you want to look at there is how much distance is there on the vertical axis. So let's look at what they say in the paper here. I've exerted this. A difference in log E, so that's just, not that, that's just this vertical axis here. Where is it? A difference of less than 1 is insignificant, and a difference of between 2.5 and 5 is strongly significant. Okay, so what's the difference here? We're told less than 1 is insignificant. So what's the difference here? Well, let's take green and red. So green is 454, and red is, well, what's that? At its lowest, it's 453.5. Now, so that's a 0.5 difference. That's insignificant. And in fact, even if you go from here right down to here, that's 1. So the point is, essentially, all of the comparisons here are insignificant. And also, I should mention that the more negative values represent a better fit. So you're actually looking at a higher on the graph is a better fit. So I would say that actually lambda CDM is a slightly better fit than the HC, where I think the blue one is more appropriate over most of the values here. But if you choose the red, they're basically the same. But they're all of these are insignificant because, as it says here, a difference of 1 is insignificant. And it mentions this in the paper. The difference is not significant. So what's the upshot of all this? The upshot of all this is that this paper is a model fitting exercise, which shows that there's no significant difference between similarly parameterized models for the holographic cosmology and for standard non-holographic models. So that doesn't show any empirical support for anything. It's sort of interesting as a methodological exercise. I don't want to say there's no value to the paper, but it does not support the idea that the holographic cosmology models are better than the standard models. And certainly it doesn't support any of the metaphysical claims or ontological claims that IP wants to make on the basis of them. So I'm not ragging on the paper so much, but the implications that IP is drawing on it are just not correct. There's no significant difference between the models. And even if there were, it's not clear what that would even mean because it's just a model fitting exercise, which there's no clear even interpretation of what the holographic cosmology would mean because it's just a correspondence between the gravity in the bulk and the field theory on the boundary, which doesn't have any very clear ontological interpretation or philosophical interpretation anyways. All right, so that's that. Now let's keep going.
Radiation infers three-dimensional reality is an emergent informational construct. Observable evidence infers reality as we experience is not fundamental, but emerges from the quantum realm. This piece of data only correlates to a study from later that same year, which points out entanglement is an inevitable feature of reality. Entanglement happens when two particles interact in a way that their quantum state or wave function cannot be described independently or without the other. However, if you were to separate them by a great distance, a change to one instantly affects the other. This has been demonstrated in several experiments, and now a new study shows that such a phenomena is an inevitable feature of reality. We show that any theory with a classical limit must contain entangled states, thus establishing entanglement as an inevitable feature of any theory superseding classical theory. In other words, any theory which purports to describe reality must include quantum entanglement as an underlying fundamental feature of reality. If you entangle two particles and separate them by a great distance, a change to one will instantly affect the other, regardless of the space between them. So the information between them doesn't seem to be affected by space. Implying space is not fundamental for the underlying world of quantum mechanics, but an emergent phenomena of the classical world that only exists after measurement.
Whereas space is just obviously not fundamental. Space is something where when you go from classical mechanics to quantum mechanics, space more or less disappears. In classical mechanics, what do you have? Some particles moving through space with some velocity. In quantum mechanics, you have a wave function of all those particles. And that wave function, we tend to talk a language that the wave function is a function of all the particles and their locations in space, but we don't have to talk that language. We can use what is called the momentum space description. We can completely describe the particles by how fast they're moving instead of where they are in the universe. And for that matter, we don't need to use any description at all. We can just use these quantum mechanical states in their own right with no reference to space whatsoever.
Remember that in quantum mechanics, prior to
All right, so let's take that quote from. We'll come back to entanglement a little bit later, but the quote there from Sean Carroll is an important one. Now, it's a bit complicated here, so I want to be careful what I say. Sean Carroll does believe that space is not fundamental. I actually mentioned this briefly in the debate as well, but when Sean Carroll says that space is not fundamental, why is that not coming up? He doesn't mean anything like what IP thinks when IP says that space is not fundamental. But what I wanted to do just here specifically is take a look at the context of what Sean Carroll is saying there, because again, I think that the implication you get from just watching the quote in the video is not the implication I think that Sean Carroll was trying to make, the point that Sean Carroll was trying to make. So let's have a look at this. I've taken this, so this is just a link to the original video. I'll eventually put all these in the comment section here so you can check this out for yourself. So the question that was asked of him was, why do I think, that is, why does Sean Carroll think, someone is asking him this, that space is more likely to be non-fundamental than time? Which is interesting because we've actually got someone else who says the opposite. But anyway, let's leave that for the moment. So here's Sean Carroll speaking. For one thing, quantum mechanics intrinsically treats time and space very differently. The fundamental equation of quantum mechanics, Schrodinger's equation, has time in it, but it doesn't have space in general. So there's a chance that time really is fundamental for that reason. So this is correct, and this is sometimes called the problem of time. So like Schrodinger's equation, quantum mechanics has time as a key variable in it. There's many forms, there are different forms of Schrodinger's equation, but it does have time as a key sort of variable that you can solve the equations, and the time dependent versions, the solutions then change over time. Whereas for general relativity, time and space are just sort of, I guess, fused together to form the four-dimensional space-time manifold, which is then distorted or bent by massive objects. And so they treat time, the two theories treat time quite differently. So that's all Sean Carroll is saying here. Time appears to play an important role in quantum mechanics, but whereas space doesn't. And so there seems to be some difference there. Now, why does that matter? Well, let's keep going through the rest of this answer. The Schrodinger equation might not be the right description, so that's why we are still not certain. So he's saying we're not sure there, but there's a hint there that maybe time is more fundamental than space there. But there's at least a fighting chance. Whereas space is just obviously not fundamental. Notice that this is the point right there is where IP's clip starts, where space is just obviously not fundamental. Space is something where when you go from classical to quantum mechanics, space more or less just disappears. In quantum mechanics, what do you have? Some particles moving through space with some velocity. In quantum mechanics, you have a wave function of all those particles. And then he continues, I won't go through the rest of that quote. So what point is Sean Carroll trying to make here? The point he's trying to make is just that he thinks that, Sean Carroll thinks that space is likely to be not as fundamental, because in quantum mechanics, you don't really see space as a fundamental thing. Like you can represent a quantum or many quantum systems in terms of where the particle will appear in space. But as he says in the quote, you don't have to. You can use momentum space, for example. Whereas time is fundamental to quantum mechanics, like it appears in the time-dependent Schrodinger equation, and you can solve over time. That just isn't the case for space. So that's what Sean Carroll is saying here. When he says space is just obviously not fundamental, he's talking about in the context of the Schrodinger equation. I think that's very clear from this quote here. He's not saying that space is obviously not fundamental in the context of like cosmology. Now, I understand that Sean Carroll thinks that space and time probably both emerge from some sort of underlying, or at least space. I think space and time, though. I'd actually have to check that. But definitely space emerges from some sort of underlying quantum system. We'll actually look at that in a moment, what he has to say about that. But all I mean is in terms of this specific quote, it's clear that Sean Carroll, from the context, is thinking about the relationship between time and quantum mechanics and time and space. Sorry, let me say that again. He's talking about the relationship between time and quantum mechanics and space and quantum mechanics. And he's saying that space is obviously not fundamental for like the Schrodinger equation, quantum mechanics, because like that doesn't appear there, whereas time does. That's the point he's making there. So I think that that's important, because when he says like it's obviously not fundamental, that seems like a strong claim, but he's talking about it in a very specific sense in the answer to the question why I think that space is more likely to be non-fundamental than time. So again, I'm trying not to misrepresent Sean Carroll, because I think that he does think that the universe is emergent in some sense, but from this quote, he's not really even talking about that. He's talking specifically about drawing implications from Schrodinger's equation. All right, let's continue on with the video then. So again, I think that quote's dubious. Like you could maybe use it to support to some extent, but I think you just need to understand the context that Sean Carroll was talking in, like what he was trying to get at when he says it's obviously not fundamental. What's obvious there? It's obvious when you look at Schrodinger's equation. That's what he was saying.
Measurement. Particles have no defined properties or locations. In the absence of measurement, particles simply exist as a wave function of possible states they could take, and that includes the location of the particles. If particles have no defined locations prior to measurement, that would mean the information between entangled particles exists other than spatially. Spatial location only emerges after measurement. Thus, entanglement shows space is not fundamental, but emergent from quantum processes, correlating with the evidence from the holographic principle. The wave function of entangled particles is far more fundamental than the space between them.
So that's kind of what Sean Carroll was saying, because the Schrodinger's equation doesn't have like the space between particles as part of it, whereas it has time. In fact, you could even see it here in the form that IP's put up here. It's got the derivative of the wave function with respect to time. Now it does have spatial derivatives as well, but it turns out you can represent the wave function in different, like you don't have to use position space, which is the form here. You can use like momentum space, for example, which again Carroll mentioned in his quote. Whereas time, that in the time dependent form, you can't get rid of that. At least not in like, it's a bit different if you start talking about quantum field theory, but we're just talking about like traditional non-relativistic quantum mechanics.
Therefore, the underlying information is more fundamental, and space is emergent.
Claims like that are just very vague. So I'm not really going to address vague claims like that, which I think are just like too hard to even assess. I'm just going to focus on like quotes from physicists and papers that he mentions.
Space is just the illusion that particles are separated, not a fundamental feature of reality. Physicist Sean Carroll writes on his blog, Space Emerging from Quantum Mechanics, that the most likely way to explain the nature of gravity is to note space emerges from quantum mechanics, not that space is a fundamental property of the subatomic world. Physicist Haiyan Seok Yang says emergent spacetime is the new fundamental paradigm for quantum gravity. This new paradigm suggests space is not fundamentally real, but emergent from the underlying quantum realm.
All right, I think that's a good place to stop. I don't know about that particular quote from the physicist, because there are lots of paradigms, and I mentioned this to IP in the debate. There's like lots and lots of paradigms in quantum gravity. I don't think anyone knows which are like the most prominent or how many people are working on each of them, because I don't know of any survey data on that. But anyway, let's look at what Sean Carroll has to say about the emergence of space-time. Now, I don't actually know if I put that in my document here. I thought I did. Bear with me, there's quite a lot in here. I thought I did have that. No, that's not it. Where is it? I got the quote from, I thought I put his model in. No, that's the other physicist. Oh, sorry. It looks like I didn't put his model in my document here. Okay, what I will do is just open that up as a separate tab. Now, what was the Sean Carroll emergence? Apologies for this. I thought it was in my existing document. I'm just going to jump back here. What was the title? The Space Emerging from Quantum Mechanics. That's the one. Because I want to explain why what IP says here doesn't follow from, I mean, emergent spacetime, or particularly Carroll's blog here, because IP said, just after quoting, like referring to Sean Carroll's blog here, he said that these show, or the implication of these models is that space-time is not fundamental, it's an illusion, or something to that effect. So let me now share this tab here, and we'll have a quick look at this. So here's the post in question. It's basically a summary of a paper that he's written. Okay, so is that the one I wanted to focus on? Yeah, so here's the essence of Sean Carroll's model here, again, as I understand it. Don't claim to be an expert, but I've read through this and I think I get part of the idea here. So what he wants to do, what Sean Carroll wants to do, is try to explain space, I think it's just space. I'd have to double check if it's time as well, but I'm pretty sure it's just space. To reduce that, basically mathematically, but then in terms of a physical theory, to the entanglement or the degree of quantum entanglement between like subsystems. So let's have a look at what he says here. David, was that how he spelled his name? I thought it was David Hilbert. Maybe I was wrong there. Anyway, so space divides up into pieces, technically factors that we can multiply together to make the whole space. So that's these little bits here. Like think of them as little, how to describe this? Little separable parts of the full description of the whole universe at a quantum level. So use quantum information, particularly the amount of entanglement between different parts of the state, to define a distance between them. So what he's doing is he's breaking up the whole quantum description of the whole universe into little pieces that can be multiplied together. So they're sort of independent from each other, separate from each other, let's say, to different extents. And then the degree of entanglement between them, which is the degree of their correlation, I guess is a pretty good way to describe that. He defines it as mutual information, but that's related to correlation, to define a distance between them. Parts that are highly entangled are considered nearby, like spatially nearby, while unentangled parts are far away. This gives us a graph. The vertices are different parts of Hilbert space, and the edges are weighted by the distance of the emergent distance between them. So that's the basic model. The argument here is that Carroll is saying that space emerges as basically at the large scale classical level as a sort of derivative in terms of the degree of quantum entanglement between little subspaces of the overall quantum state of the universe. That's his theory of where space comes from. The more entangled they are, the closer they are in space, and the less entangled, the further away they are in space. So let's have a look at this part here. It's the last bit that's the most exciting but most speculative. The claim in its most dramatic sounding form is that gravity, space-time curvature caused by energy momentum, isn't hard to obtain in quantum mechanics. It's automatic. So it comes from the degree of entanglement between the systems. If geometry is defined by entanglement of quantum motion, then perturbing the state, adding energy, naturally changes the geometry. So this is why this is so interesting, because I'm kind of skipping over a bit here, but it would explain, if this was true, why there's a connection between the geometry of space-time, and the amount of mass in the space there, because basically the mass energy perturbs the system, altering the levels of entanglement between the subsystems, thereby altering the distance between them, basically, warping the space in again, very, very crude description there. So that's why he's saying here, why there's a relationship between energy and curvature by general relativity, as shown by like images like this here. Matter curves space-time, and then matter moves in accordance with the straight lines in that curved space-time. So this is as it says here. It's wait, where did he say that? The optimistic view is that gravity just pops out effortlessly, but the devil's in the details. A long way to go before we can declare victory. So this is still preliminary stuff, right? I think that's what I wanted to say here. What we've done is extremely preliminary and conjectural. We don't have a full theory of everything, and even what we do involves a great deal of speculating. Is not enough rigorous calculating. So that's fine. I think that'll do us for the moment. Oh, wait, is there anything holographic principle here? Just seeing if there's anything else I wanted to mention. Okay, good. That'll do us for now. So now, why is that all significant? Well, basically because Sean Carroll here is saying that according to his theory, which again is speculative, but okay, fine, there is space, at least space, I'm not sure about time, but at least space is emergent from, or like derivative from, entanglement between like subsystems of the overall quantum state of the universe. Now, that's very interesting. If that were true, that would be a very significant result. But it doesn't mean that it's not real. And that's the real issue when it comes to what IP is saying, apart from presenting this as sort of more definitive than it really is, although that's, I suppose that's an emphasis and you can argue about that. But let's just again review what IP claimed about this. Oh, bugger. Hang on, I forgot if I shared audio or not. Now I'm paranoid about that. Let me just do that again. I may have done, but I've got to make sure that I do consciously, otherwise I'll screw it up. Okay, let's just jump back a bit.
Particles are separated, not a fundamental feature of reality. Physicist Sean Carroll writes on his blog, Space Emerging from Quantum Mechanics, that the most likely way to explain the nature of gravity is to note space emerges from quantum mechanics, not that space is a fundamental property of the subatomic world.
So that's fine.
Physicist Haiyan Seok Yang says emergent spacetime is the new fundamental paradigm for quantum gravity. This new paradigm suggests space is not fundamentally real, but emergent from the underlying quantum realm. But it is not just space that is emergent from quantum entanglement. Einstein demonstrated.
Okay, so what he said there is that this shows that space is not fundamentally real. So the thing about that is that I feel like it's misleading there. It depends whether you emphasize the fundamental or the real. Sean Carroll is not saying that space isn't real. He's saying that it emerges from something more fundamental. So if you say fundamentally real, then that's fine. But remember, according to the same physical definitions here, and again, I did mention this in here with the debate, every macroscopic object is not fundamentally real because it doesn't exist at the most fundamental levels of like physical description. So, people, life, bookshelves, computers, planets, all of those things aren't fundamentally real at the physical description because they emerge from, lower order phenomena, which is fine if you understand what is being said. Now, the concern there is that the picture that he's painting in these videos, the language that he's using, the visuals and everything else is to imply that the emergent gravity results, the results from this emergent spacetime stuff are pointing towards or providing evidence in favor of the simulation hypothesis, or at least his IP's version of theistic idealism, which would say that space and time and everything in it aren't real in a physical sense, like they're real, but they're ideas in God's mind, or some sort of simulation in God's mind, which IP has also said, right? So that's a very, very different claim to saying that, well, gravity is just, and space is emergent from underlying quantum, stuff that's happening. Again, the physicist says that everything that exists in the universe, like, all macroscopic objects are emergent from lower order physical stuff. So the fact that gravity in space might also be is very interesting, but it doesn't really do anything to lend credence, I would argue, to the actual contention that IP is driving at here. So in that sense, I think he's misrepresenting what the science is saying. It doesn't really entail any of, or really even support any of the conclusions he's sort of trying to get out of it.
Space and time are one. So that would have to mean that time is also emergent from the underlying quantum realm. And an experiment from 2013 reveals this. The Wheeler-DeWitt equation, which calculated the wave function of the universe, noted the time factor dropped out, meaning time is also not a fundamental aspect of the underlying quantum world, but emergent in the classical world that we experience day to day. And in 2013, an experiment seemed to confirm this idea that time, along with space, is an emergent phenomena.
So in quantum gravity now...
Oh, okay, so that's a misleading cut, because what she is saying, her name is, sorry, I don't remember it. I've got it written down here. Fotini Marco Paolo, I'm not sure. I'll just call her Fotini because I can at least go pronouncing that. Anyway, she has some very interesting ideas, but it's nothing to do with the paper that IP just mentioned. So before we actually, let me just jump back here. Yeah, because that's what I want to talk about now. So this paper here, Time from Quantum Entanglement and Experimental Illustration. So IP claims that this is evidence that time is also not fundamental, or like it's emergent. Now, again, this might be the case, right? But the point here is just to look at the science specifically and the claims that IP is making on the basis of that. So let's now take a look at this paper. Okay, I have to share back the document now. I wish I could share two things and flip between them, but I don't think I can do that. Okay, so I've taken out a couple of excerpts from this paper here. What does this paper say? Is this an experimental evidence that time is actually emergent or derivative in the way that IP says? The short answer is no, it's not. What does this paper actually say? Well, this paper is, actually, I think this might be a good way to describe this here. So people have proposed that time might be emergent, it might not be fundamental. And there are a couple of mechanisms that have been proposed for that. They actually investigate two in this paper, what they call POR and GPPT. But for our purposes, I'm not really going to distinguish between those. Now, what's the basic idea here? The basic idea of these mechanisms is that you could have a quantum system which overall doesn't change. The overall description of the system doesn't change. But again, the language is tricky here. The sort of subcomponents of that system change with respect to each other. So you can kind of define time as one bit of the system changing with respect to the other one, even though overall it doesn't change when considered as a totality. So this relies on the way that the system is observed, because remember, IP talked before about entanglement, which is like two quantum things are kind of correlated with each other, and their behavior affects each other in some sense, at least. So if you're looking on, right, imagine I've got two particles that are entangled. If I'm looking on as an outside observer, the system might be constant, right? There's just those two particles and they're just like moving or oscillating or whatever they're doing. The description of the whole system might be static. However, within, if I'm now imagining myself as one of the particles within that system, and so let's just suppose they're oscillating sort of up and down, which is kind of what happened in this example, right? So if I'm one of these particles and I'm oscillating, then there's a correlation, actually a one-to-one correlation with what the other particle is doing. So if I oscillate up, the other one goes down. And so we sort of go directly out of sync with each other, like a sine wave and a cos wave, if you want to think about it like that. That's actually kind of what's shown on this diagram here. So I can define, or you can, if you want to, define a time variable as basically how one of the subparts changes with respect to the other one. You don't need any like outside external time. It's purely in terms of, the rate at which I change with respect to the other thing. That's my time variable, right? But the outside observer doesn't see that. The outside observer just sees a static system. But if you sort of then enter into the system, you can define time in terms of the change of the other particle. That's the very loose idea here. Now, how is that relevant to anything? Well, this is the basis of a theory according to which basically time could be an emergent quantum process, essentially, or can be emergent from quantum process is probably a better way to say it. Now, I won't try to describe the details of the experimental setup, but note here, they talk about super observer mode and observer mode. And this is what I was saying before. There's sort of two ways to look at the system, and that corresponds kind of to these two diagrams. In observer mode, you can see what one of the particles is doing and then relate that to what the other particle is doing. So when one particle is sort of at a 1, the other's at a 0, and then they kind of move between the two states, and then you can define a time variable as the relative motion of the two particles. But when you observe the system in the super observer mode, where you don't see the individual particles, you just see the sort of whole system as a whole, it doesn't change. And that's kind of what this is showing here, that there's basically a flat line. I won't try to describe precisely what this is, but it's just illustrating the point that there's different ways to observe the system. And then if you sort of, if you are outside of it, it just looks static. But if you kind of enter into the system and observe the parts of it, it's sort of fluctuating, and then you can define time as the rate at which sort of one bit of it changes with respect to the other one. So that's what they're saying in this conclusion here. Our experiment is a practical implementation of these mechanisms, but obviously it cannot discriminate between these and other proposed solutions for the problem of time. The problem of time there being what I mentioned before, that basically it seems that the way time is treated in quantum mechanics and in general relativity is very different, and how do you reconcile them? So they're saying it can't discriminate those. It's just an illustration of the mechanism. It doesn't prove that this is real. It just proves that the basic idea could work. And this is basically what this is. This is like a toy model. It says, hey, we built a system that actually does the thing that people have been saying could happen. But it doesn't show that this is what actually is the case for the real universe. It's an illustration of the idea. That's all it is. I'm just seeing if there's anything else I wanted to say here. Without any reference to an external time, but only from measurements of correlations between clock photon and the rest. So that's how they're able to illustrate these time-dependent graphs from, I think that's this figure here. They are an implementation. So this setup is an implementation of a relational measurement of a physical quantity relative to an internal quantum reference frame. So the point is, this system shows you don't need any external time reference to get something that appears to behave like time by the internal changes of the quantum system with respect to some other part of the quantum system, but an outside observer wouldn't see any overall change. So this is an illustration of a mechanism. It is not experimental evidence that this actually happens like in the real universe. So it's still very interesting, right? But it's not really what IP said it was. It's not evidence that time is emergent in the universe. It's just evidence that the mechanism that's something like the mechanism that was proposed can occur in at least this experimental setup, right? Whether it can occur for like the universe as a whole, well, that's really quite a different question. Okay, now let's go back to the video and keep going.
Confirm this idea that time, along with
what's going on.
So now there's this physicist here.
Probably what's going on is what we're seeing is that the whole notion of space and time is probably not really fundamental. So
that sounds incredible. That space and time is not fundamental. Space and time seem, in an ordinary sense, to be the most fundamental thing, and everything else seems to happen in space and time as sort of the fixed background.
Right. But what could be happening is that there are two different notions of time, a more fundamental one and an emergent one. So it's the emergent one that is part of space-time, but there is a more fundamental one that makes sense without space.
Now, neither one of those new ways are obvious to us in our common perception, obviously. But Einstein put space and time together, which was a radical change. What you're saying is that the time that he might have unified with space may be an emergent time,
That's
and there's
right.
something more
There's a
fundamental
more
in time.
fundamental one.
Thus, all of what we experience, space, time, matter, all seem to be emergent constructs of the classical world, not fundamental aspects of reality. Experimental data shows us matter and space-time are emergent, while in contrast, another experiment...
All right, let's pause that there. So I don't know if I'm going to go through Frattini's theory about the emergence of space. It shares a lot of similarities with Sean Carroll's, but I mean, it's a different theory. It's more of a geometric theory than so it doesn't rely on entanglement. It relies on a geometrical conception. I explained this a little bit more detail in the debate, so I think I'll just pass over that just because I want to keep things focused. And broadly, the point is the same as the Sean Carroll case. What she's saying in the video here makes it sound like that her model supports what IP is saying, but I don't think it really does. It is just another model according to which space, or actually in this case, it's just space, not time. Space emerges as a result of a low energy, well, what she calls is geometrogenesis. So emergence of geometry, basically, from an underlying geometric interaction of what she calls micromatter. So you can think of that as like some quantum stuff, right? At a high level, that exists at a high energy level, like very early universe, that exists non-spatially. Everything's basically in the same location, if you want to put it crudely, and tightly interconnected. But at low energy levels, as the universe cools, it separates out and becomes localized, and you get the origin of space, which she calls geometrogenesis. So that means, again, according to this theory, that space is not fundamental. It emerges from underlying quantum processes. Again, analogous to what Sean Carroll was saying, but the specifics are different. Now, that does mean that space isn't fundamental, so that part is correct, but it doesn't mean it isn't real or that it's an illusion. It just means, like life and bookcases, like behind me, and planets and anything, pretty much anything else as a macroscopic object, it doesn't exist at the most fundamental level of our physical models. That's all that is meant there. It doesn't have any further implications about whether it might be emergent, like from something other than the underlying quantum state, or that it's like a simulation or an illusion or anything of the sort. All right, back to the video.
Shows the
I'll
wave
just
function
jump back a couple of
all seem to be emergent construct of the classical world, not fundamental aspects of reality. Experimental data shows us matter and space-time are emergent, while in contrast, another experiment...
So there is no experimental data that shows that. Remember the two that we looked at, the one was just saying that was the model fitting exercise, which showed that the holographic cosmology was basically like just as good a fit as the standard model. That's not evidence for it. It just says, well, it's not inconsistent with the data, at the very least, at least not with that data. The other thing was the emergent time experiment, which wasn't evidence that time is actually emergent. It was just evidence that you can construct an experimental apparatus that illustrates the mechanism or an analogous mechanism that's proposed for it. Neither of those are experimental evidence to support the idea that space and time are emergent. So at the moment, this is just levels of scientific hypotheses. It's not established physics, which is fine. Like, there's nothing wrong with that in terms of physics, but it's wrong if you're then going to build a philosophical system or argue that it supports a philosophical system.
Experiment shows the wave function is fundamental to reality. At the advent of quantum mechanics, many suggested the wave function was not actually a part of nature, but just a mathematical tool which represents our lack of knowledge about the system. Yet a recent experiment gave strong evidence the wave function should directly correspond to reality. So the wave function, a mathematical probability of possible states in Hilbert space, does correspond to the fundamental nature of reality. Space-time is nothing more than a construct emerging from the wave function in Hilbert space.
All right, so that there I think is wrong. Okay, so these emergent space-time models don't show that space-time is a construct. They show that it's emergent. A construct, I guess you can argue about that. It seems to me though a construct would be something that is like man-made. I think that would be fair. Or that it is like subjective. It's something we come up with. So interestingly, as a nominalist, I would say like mathematics is a construct. It's something we invent and then use for applications. I'm not saying you have to agree with that, right? But I'm just using that as an example. If you don't think that, maybe language or money would be examples of constructs. Governmental systems or like any artifact, right? Those are constructs. Laws of nature you might think are constructs, or perhaps you think they're fundamental. But the point is, space-time may or may not be a construct, depending on how you think about these sorts of things. But emergent space-time models don't show that it's a construct. Emergent space-time models show that it is not fundamental. It's derivative from underlying processes. That's all that it says. Now, that being said, let's talk about this paper here, Measurements on the Reality of the Wave Function. Now, it's interesting because in my debate, IP actually presented another paper, well, a completely like a philosophical paper, which objected to my claim that quantum fields might be like fundamental, a quantum field ontology, which is something that I'm sort of experimenting with and thinking more about. So I feel like that kind of contradicts what IP's argument here, but that, I mean, that's fine. He can change his mind, but I just want to comment on what this paper actually says. So does this paper show or like prove that the wave function is real? Well, shockingly, no, it doesn't. But let me explain. Okay, you may have sharp-eyed watchers may have actually noticed that. Actually, let me. Oh, I can't do that when I'm sharing this. We'll show at the moment that in the very conclusion that IP put up on the screen, it contradicted what he was saying, or at least if you don't want to use the word contradicted, sharply modified the interpretation of what IP was claiming. I'll be careful here because if I say contradict, it's like, well, actually, you can interpret it this way where it doesn't contradict, but you know, we can have those debates all day. Anyway, so what does this paper actually say? So there's different views about what the wave function is. So-called ontic views and epistemic views. So let's look at this diagram here. This is illustrative to make the point. So phi here is being used to represent the quantum state. So you can think of that as the wave function if you like. So in this case here, subgraph B or subfigure B, in the ontic model, ontic means like existing. So in the version according to which the quantum state is like real, the distributions are disjoint for any pair of non-identical pure quantum states. So here are our two quantum states, right? And here's a lambda here. Now, what is lambda? Lambda represents the underlying. Does he define it here? Yeah, here it is. The underlying ontic state. So whatever it is that's real, that's what lambda is. So you can think of it as like a parameter that measures some real thing. In practice, there's perhaps going to be multiple dimensions, but this is just a simplified version, right? So this framework assumes that there is an underlying like true ontic state, something that exists, and the wave function then is a description of that system. So you can see here are our two different quantum states, and they have different values of this whatever this variable is here that's being measured, like some physical thing that you could. Well, actually, this doesn't have to be measurable. I should be careful there. This is just something that defines the nature of the quantum system. And then these are the two wave functions corresponding to two different systems. So that's the ontic model. Now, here's the epistemic model. See here. Notice the difference that these distributions overlap. So that means that here's the key point here. This took me a little while to work out what the point of this is. Under this model, the epistemic model, so C is epistemic, B is ontic. Under the epistemic model, you can have the same quantum states, the same lambda, look here, same lambda, consistent with two different wave functions or descriptions of the quantum state. So it could be either one in this range here. Now, down here, it's only this one, and up here, it's only this one, but there's a range where they overlap. What does that mean? It means that, again, to put it crudely, the wave function is not fundamental. It's only a description because there's the same quantum state that has two different wave functions. So the wave function is not fundamental because there's two different ones that can describe the same system. Can't be fundamental. So it's just epistemic. It's a tool that we use to understand things. Whereas in this model, they never overlap, is the claim, for pure, non-identical, pure quantum states. They never overlap. So there's like a one-to-one. If I tell you the lambda, you can tell me the wave function that describes that. That's the ontic model. So that is what this paper says. This paper shows that, well, sorry, it's a little bit more than that. This paper shows that this epistemic model doesn't work. I actually didn't really follow the details of exactly that because it doesn't really matter for our purposes, because we can accept that result and what IP says doesn't follow. So what it says is that this doesn't work. You like a big cross through that. You can't hold to this. You've got to hold to this. Does that mean that the wave function is real? No, because if you've been paying attention, notice we've assumed this lambda here. And it says this clearly in the introduction. Assuming that the notion of objective reality exists, our results strengthen the view that the wave function should correspond directly to this reality. This means that they're assuming this lambda here. They're assuming that there's an underlying quantum state. And what they're saying is the wave function, there should be a one-to-one correlation between those. This is clear again here from the end of it. Recall that the ontological model framework covers all interpretations of the quantum wave function in which there is an observer-independent objective reality underlying quantum mechanics. That's this lambda here. Within these realist interpretations, our results conclusively rule out the most compelling phi epistemic models, namely those that fully explain quantum indistinguishably by overlapping probability distribution. So that's this. They're ruling this out. Boom. Cross through it. But the point is, this is assuming that there's an underlying real quantum state. So it's misleading for IP to say that this somehow proves the reality of the wave function. It proves the reality of the wave function if you assume that there's a real underlying sort of quantum state. Now, I tend to think that I tend to subscribe to that, right? As a realist and for other reasons, I lean in that direction. But the point is, if you can't use that study to prove that point, because it assumes that there's a real observer independent reality to it, and just says that epistemic models within that framework won't work. What I wanted to show here is that, hang on, where is it? Oh, I went back too far. He shows this. Sorry, here it is. This is just what I was showing before. Assuming that a notion of objective reality exists, and that's a specific notion, right, at a quantum level, our results thus strengthen the view that the wave function should directly correspond to this reality. So it doesn't prove that the wave function is real. This study is evidence supporting an ontic interpretation of the wave function, assuming that there is an underlying observer-independent state. But there are interpretations of quantum mechanics that would just deny that or be disinterested in the question. They just say, look, we don't know whether there's an underlying state. We're just going to treat quantum mechanics as a way to get experimental predictions. Like quantum Bayesianism would be an example of that. It would just flatly deny this whole, as far as I understand it, would deny the whole lambda thing. Like, no, what are you talking about? This real underlying quantum ontic state here that you can never measure. We don't need to worry about that at all. We're just going to look at the experimental predictions. So this study doesn't refute something like that. Hopefully that was somewhat clear. So again, IP is overselling what this paper says.
Should directly correspond to reality. So the wave function, a mathematical probability of possible states in Hilbert space, does correspond to the fundamental nature of reality.
Yeah, if you assume that there is an observer-independent, objective, underlying quantum, underlying state of any quantum system, that's what this is assuming there. That is missing here, which is kind of important because it seems like that IP is saying that this study shows that that's the case.
Space-time is nothing more than a construct emerging from the wave function in Hilbert space.
Space-time is not fundamental. That space-time is, if you like, an effective emergent description from something else.
The implications of this are quite astonishing, because the wave function is not a physical object extended through space, but a mathematical probability of where physical particles will appear in space. Sean Carroll explains.
That's one like application or interpretation of the wave function, but it really could describe all aspects of a quantum system, not just where it will appear in space. But I mean, that's a bit of a nitpick, but it does matter because remember that before Sean Carroll was talking about how space is not fundamental to quantum mechanics because you can work in space in the space description or in the momentum space. But to say that this is what the wave function is sort of implies that space is fundamental to it, which is a bit in contradiction with, or at least in tension with the whole point of what Sean Carroll was saying before.
Mathematically, wave functions are elements of a mathematical structure called Hilbert space. That means they are vectors. We can add quantum states together, the origin of superpositions in quantum mechanics, and calculate the angle, or dot product, between them. The word space in Hilbert space doesn't mean the good old three-dimensional space we walk through every day, or even the four-dimensional space-time of relativity. It's just math speak for a collection of things, in this case, possible quantum states of the universe.
Yeah,
the underlying truth of the universe is a mathematical reality from which the classical world we experience emerges. What we think is objectively real is nothing more than an emergent construct of underlying mathematical informational processes.
Okay, so this is where he's really going way beyond here, right? What he says, what we think is real is nothing more than a mathematical construct or a construct of an underlying mathematical something or other. Now, that it just is not, it does not follow from anything that he's presented, as I've shown, I think. At most, even if you think that all of these emergent space-time theories are correct, and we don't even know that, but suppose they were, it would just show that gravity is not, and space, maybe time, are not fundamental. They're emergent from underlying quantum stuff. That doesn't mean that they're like an illusion or that they're not real or that they're a construction. Nor does it even mean that space and time emerge from mathematics. I don't even think that really makes any sense. Because at least let's talk a little bit about mathematics. You might be like me, an anomalist about mathematics, where according to which mathematics is like a construct that humans use to think about things, and we apply that in different, for describing different parts of reality. Or maybe you're a Platonist. You think that there are these abstract entities that our mathematical language corresponds to. And therefore, there is a mind-independent reality to mathematics. But in either case, mathematics doesn't have a causal effect on the world. not in any direct way. I mean, I guess you could say, well, what I think about some mathematical theorem might affect what I do today, but that's not a direct effect. That's an indirect effect, right? That's my belief about something. But Platonic forms don't have causal effects. Neither do like constructs, like human constructs, in the way that I'm the nominalist would think. The point there is that in either of these conceptions, it wouldn't really make sense to say that space-time emerges from mathematical information. That just doesn't really make sense. Mathematics doesn't cause things to happen. It describes things. Even if you're a Platonist, it doesn't cause things to happen. Now, there may be different views that do allow that to happen, but like mathematics to cause the universe or something. But to me, that just doesn't even make sense philosophically. So this isn't really IP misrepresenting science at this point. It's just I don't even really know what he's saying. But certainly science doesn't say anything of the sort. Let me just replay what he said there.
Of the universe. The underlying truth of the universe is a mathematical reality from which the classical world we experience emerges. What we think is objectively real is nothing more than an emergent construct of underlying mathematical informational processes.
Yeah, so none of the theorems that he's quoted or experimental evidence supports that. And it's not even clear that it makes sense philosophically. I mean, maybe you can make sense, but I think there's a lot of work to be done to make sense of what that would mean, that the whole universe emerges from a mathematical something or other. I mean, I guess you get to theistic idealism. That's, I guess, how you would understand that. But the science doesn't show that.
To further confirm this, Brian Whitworth looked at specific features of our universe and compared them to a virtual world. What he found was 11 key features of the universe are better explained with the idea of a virtual reality instead of an objective reality with fundamental space-time and matter. Features of our universe, like the maximum speed, the Big Bang, quantum transitions, and wave function collapse, all make more sense in a virtual world. In other words, the philosophical conclusion is our universe behaves more like a virtual world instead of an objective reality. This aligns with the scientific data we just discussed, which shows space-time and matter are emergent. On top of this, the work in theoretical physics is leading us...
Oh, wait, hang on. So those were the graphs from the paper I was talking about before. Yeah, so I knew we showed them somewhere. He just, for some reason, puts them here.
And matter are emergent. On top of this...
So those were the graphs I was talking about before. So this does not support the holographic principle. It just says that models based on it can explain the anisotropies in the power spectrum of the cosmic microwave background radiation to this roughly the same degree as standard models, and that really doesn't really prove much of anything. Now, jumping back a little bit about this, about this about this paper here.
To further confirm this, Brian Whitworth looked at specific features of our...
This one. Now, most of the papers that he's been citing are perfectly valid, legitimate, good scientific papers. They don't, I think, show what IP says that they do, but there's nothing really wrong with it. This is not in that category. This is just nonsense. Let me be rude here and say it's just nonsense. I'm going to go through this quickly because we talked more about this in the stream I did with Nathan, and I just really don't want to give this paper too much attention. So I'll just briefly explain why it's nonsense. Okay, so this is not really a scientific paper. It's a bunch of speculation by, I think the guy's a data scientist who's decided to start talking about the foundations of quantum mechanics. Now, I mean, I'm not a physicist, right? Although I do have physics background, I don't think this guy does. But it's not really the point that he's not a physicist. It's just that when you see that someone is making very big claims in a field that they're not an expert in, you should take notice of that. I try not to make big claims about fields I'm not expert in. I just try to make modest claims or say, well, look, there's a theory that I find persuasive that a bunch of people in that field also argue for, so I feel justified in that. But that's not what this is. It's some guy just making up a whole bunch of stuff that he doesn't really know about. And it's not an empirical paper. It's just a bunch of speculation. So let me show an example here. This table, which supposedly shows a correspondence between aspects of a virtual reality and various aspects of the physical world. And I've just shown some of my annotations here. But there's just so much silliness here. And I don't think IP mentioned this in the most recent debate. So I hope he walks away from this because this paper is just so silly. I'm going to make this big because I'm just worried you might not be able to see it. So let's just look at a few of these quickly. Virtual particle, let's start on the right-hand side. The Big Bang. The universe was created out of nothing by a Big Bang in a single event that also created time and space. As I've noted, that's not what the Big Bang theory says. The Big Bang theory describes how the early universe emerged from a state of very high temperature and density and so forth. It doesn't actually say that the universe was created out of nothing because it doesn't go back that far. Ultimately, when you get to the Planck scale, you have to start looking at the quantum effects of gravity, and we don't have a theory for that. So already off the ball. This just isn't what the Big Bang Theory says. And a few moments on, maybe a few minutes on Wikipedia will show that isn't what the Big Bang Theory says. Now, how does that relate to virtual reality? Virtual worlds must begin with an information influx from nothing that also begins VR time space. But that's not even right about virtual worlds. Like, virtual worlds don't begin from nothing. They begin with information that's stored in some, generally a digital information storage like RAM or your hard drive or something like that. Now, I guess he means nothing in terms of the simulation, but I mean, maybe that's why it's in inverted commas there. But then that just doesn't have anything to do with the Big Bang Theory. The Big Bang Theory doesn't say the universe was created out of nothing. Let's look at the next part. Again, we'll focus on. Actually, let's go to the speed of light. I don't want to get this focused too much on this. Just make a point as to why this paper is not worth paying attention to. Light speed. The speed of light is a fixed maximum for our universe, and nothing in our space-time can move faster. That's mostly true, although it should be pointed out that current theories actually say that nothing can accelerate beyond the speed of light. It doesn't actually say, it doesn't definitively rule out particles that always travel faster than the speed of light, whose name is escaping me for some reason. Why can't I think of the name of it? Oh, it will come to me in a moment. But anyway, I mean, that's basically fine. But what does he say this relates to in terms of virtual reality? Events in VR world must have a maximum rate limited by a finite processor. And that makes no sense at all, because if you're in a virtual simulation, if you're in a simulation, there's no time outside of the simulation. So each instant in the simulation just follows from the next one. It's not like you could define a rate of the simulation in terms of something outside the simulation, unless you're outside the simulation, right? It's like asking at what rate does time pass if you're in The Sims? Well, it just passes at the rate of like one sim moment per sim moment. Like, what does that even mean? Like, what does it mean that there's a rate at which events occur? And the relevant comparison there would be to say tachyons. Thank you. That's the name of the theoretical particle that always moves faster than the speed of light. So tachyons are not definitively ruled out. We don't think they exist, but they're hypothetically possible. Anyway, in a virtual reality world, an object can move at any arbitrary speed, and in fact, it can disappear and reappear on the other side of the virtual reality. I mean, you can do that in a game, right, or in another simulation. God could do that in a simulation if the world was simulating his mind. So that actually conflicts with the fact that the speed of light is supposed to be maximum. I don't at all see how that's consistent with it. Let's look at matter and speed effects. That's one of the silly ones here. Space curves near a massive body and time dilates at high speeds and also near massive objects. Okay, that's special in general relativity. So let's see what that relates to in the virtual property. Processing load effects. If a virtual processing network is overloaded, its processing outputs must be reduced. Okay, sure. If you have a processor that's overloaded, then it will have to, there'll be a queue and your computer slows down, right? But a couple of points there. First of all, if you're in a simulation that's simulated by that processor, you probably wouldn't notice that, because like you're not going to render the next frame until everything's ready. And so it's not like that you could somehow, if you're in the simulation, see that there's been some sort of external delay between rendering one frame and rendering the next frame, because you don't experience that time. It's just one frame after the other. So how would you even know if there's a load effect there? You'd only know if you were outside the simulation. But more to the point, what does matter have to do with the load on the processor? Why would a massive object have more processor load? Like, presumably those would just be parameters that are stored in the CPU, like in the RAM somewhere, like how much matter it has. Like, if I'm writing a game, does a rock require more processing power than a feather just because it's more massive in the game, even if there's like a physics system? No, that's not how it works. Like, it depends on the number of polygons and the probably more of a graphical effect, like what sort of particle or ray tracing sort of effects I have. Like, it's nothing to do with the mass. So the point here is that I think I've made the point here. This is all speculative nonsense that doesn't make any sense, or most of it doesn't make any sense. And even if it did make sense, it's just speculation anyway. There's nothing empirical here. So to say that this paper supports anything other than like, this is the sort of thing I think I would have written as like a 15-year-old who was like, oh man, wouldn't it be cool if the universe was a simulation? And you just like write all this stuff based on a very poor understanding of the physics. It's just so silly. So I don't want to grant it any more time. I just want to say that I wouldn't even call that science. It's just nothing. And it doesn't support anything. So that's all we need to say about that. And again, I'm not saying that about the other papers, IP sites. It's really just this one that's terrible. So the others, I think, are mostly just misrepresented. So let's move on.
The universe and compare them to a virtual world. What he found was 11 key features of the universe are better explained with the idea of a virtual reality instead of an objective reality with fundamental space, time, and matter. Features of our universe, like the maximum speed, the Big Bang, quantum transitions, and wave function collapse, all make more sense in a virtual world. In other words,
They
the
don't.
philosophical conclusion is our universe behaves more like a virtual world instead of an objective reality. This aligns with the scientific data we just discussed, which shows space-time and matter are emergent. On top of this, the work in theoretical...
There's no connection whatever between space-time being emergent, even if they are, and the universe being a simulation. If they're emergent, if space-time are emergent, they're emergent from some sort of underlying quantum substrate. We don't know the details of that because it depends on the models and we don't have a final theory of gravity, but it's really nothing to do with the universe being a simulation in a computer or the mind of God or anywhere else. Now, when I asked IP about this, he just said, look, I know that the physicists aren't saying, I'm paraphrasing it. He knows that the physicists aren't saying that the universe is emergent in the way he says, but all IP claims, according to him, is that, or all he is claiming that is that what they're saying is consistent with what he says. So it's just an illustration that they believe the same thing, that it's emergent. IP believes it's emergent. Sean Carroll and others believe that the universe is emergent, or that space-time is emergent. Now, even though that they're using the word emergent in completely different ways, that doesn't seem to bother IP. It's just that they both believe it's emergent, and that's really all that there is to it, according to him. I don't think that's very satisfactory, because if you watch this video, I don't think that's the impression you get. So that's what I'm criticizing here. IP can equivocate further about what he means by emergent and what sort of level of support he's claiming. But if someone watches these videos, they get the impression, and I think that is the purpose of these videos, that experimental and theoretical results from physics support what IP is saying, and they do not. And that's my contention here. Even if what IP is saying is true, by the way, it could all be true, and the science still wouldn't support it. That's what I'm saying here.
Physics is leading us towards the conclusion the rules of physics and gravity are emergent from the underlying spaceless, timeless quantum realm. All the evidence infers that physical reality is not fundamental, but emergent from underlying information. But there is a much deeper...
So notice that he said specifically the evidence infers or implies that the universe emerges from quantum information. Not just that it's consistent with it, but that it implies that it does or infers. And so again, it seems that he's claiming here that the evidence does support what he's saying, not just merely consistent with it. Someone asked why I keep saying quantum substrate. Well, just because a lot of these models are specifically quantum in nature. But yeah, I could just say substrate. It wouldn't change that much.
Deeper implication here. The wave function explains the emergence of spacetime, but the same underlying mathematics has been seen to parallel conscious thought processes. Quantum superpositions do have a vague similarity to how we think and mentally operate. For example, we often hold conflicting positions simultaneously before making a final decision, like how the wave function is in a superposition of multiple states before final collapse to one definite outcome. We can bounce around between different ideas in our head, similarly to quantum tunneling. This similarity might be more interesting than we realize. In 2009, physicist Diederik Ertz took this one step further and published a paper noting that our cognitive processes can be readily modeled using the mathematical formalism of quantum mechanics. In other words, our inner mental world of thoughts, qualia, and emotions can be modeled in terms of Hilbert space in quantum processes, the same processes that give rise to space-time and matter. Many suggest this is just a coincidence, but there have been hints that it goes beyond this. Within the past few years, a number of papers have been published supporting quantum mind theory. Information processing has been reported to exist inside microtubules, and another study has shown that tubulin protein molecules self-assemble via quantum tunneling. We even have evidence to suggest that quantum vibrations are coming from microtubules.
Different photo,
Quantum
I'm
biology
afraid.
researcher Anirban Bandyopadhyay said the microtubule appears to be a fundamental information processing device in biology. More and more evidence keeps coming out, supporting that there are quantum processes in the brain, cohering with the field of quantum cognition, that the inner world of the mind should be modeled with the properties of quantum mechanics. This all suggests quantum cognition is not just a way to model cognitive processes, but directly applies to the very nature of the mind and the brain. Stuart Hameroff also points out that since the...
All right, I don't want to talk about Hameroff because that's a whole other can of worms. I'm going to steer clear of that for the moment. One point that I want to make here before looking at the main paper that IP cited. I was just thinking about this recently, I believe that IP's appeal to quantum biology, quantum mind theory, quantum cognition here is inconsistent with what he says in his, or again, is hard to square, is in tension with what he says in some of his other videos where he argues for a consciousness causes collapse interpretation of quantum mechanics. So there he seems to say, and we'll look at a bit of that videos in a moment, there he seems to say that consciousness is, or mentality or something, is immaterial something or other that causes the collapse of wave functions. But here in this video, he seems to be saying that the mind needs to be understood in terms of quantum mechanics, or the brain / the mind needs to be understood in terms of quantum mechanics as an underlying quantum process. So what Hameroff is saying is that the mind is a quantum computer or something akin to that, right? Whereas that's not at all consistent, or again, very hard to square with consciousness causes collapse, because they're basically working in the opposite directions. Consciousness causes collapse says consciousness is immaterial and is basically essential for quantum mechanics working. So consciousness to quantum mechanics, because it causes the collapse of the wave function. Whereas Hammerhoff and quantum mind theory and stuff is saying the exact opposite. It's saying that quantum mechanics gives rise to the mind, because the mind is like a quantum processor, or the brain is a quantum processor that gives rise to mental processes. They're operating in the exact opposite directions. Now, I suppose if you really wanted to, you could mash them together and say there's some immaterial substance that collapses the wave functions, and that's like consciousness, but then that allows the brain to operate as a quantum computer, which then gives rise to the consciousness that caused itself to collapse. But like, that's just so weird. That's my combination, right? That's my harmonization of the two theories. I don't know if IP would say that, so I don't want to misrepresent him here. But I guess the question is, how do you reconcile these two stories? Is quantum fundamental for cognition, or is cognition or like consciousness fundamental for the quantum? Which way does it go? He seems to argue both of those in different videos. Anyway, so that's what I want to say about the interpretation of that. Now, let's look a bit at this study he mentions here about quantum cognition. So again, I'll have to stop, share, wary of time, because I don't want this to go on too long, but I do have a few more papers to look at here. Okay, so that's this one. There's quite a lot to cover, so hopefully it won't be too rambly. Okay, so this is this is not the same paper that he mentioned, but it's a review of the same field. So quantum cognition, a new theoretical approach to psychology. So I wanted to emphasize this here. This is, I think this is taken from the same paper. I hope I've got that right. From quantum physics to quantum cognition. So these physicists and others who are applying these theories do not proceed from the assumption that there is something quantum-like taking place in the brain, but instead drew inspiration from both the mathematical structure of quantum theory and its associated dynamic principles. So IP actually mentioned that. He said, look, a lot of these people aren't actually saying there's anything quantum in the brain. They're just saying we can describe it using the same mathematics. Now, how useful these quantum models even are is an open question, but let's say they're useful, right? What does that follow? Well, what follows from that about whether the brain is quantum or not? And I would say nothing whatever follows, because just because two things are describable using the same types of formalisms, it doesn't mean that they're the same thing or even related. A good example of this might be that notions of equilibrium from chemistry and from statistical mechanics were in the late 19th century adopted into economics to describe the equilibrium in an economy, between supply and demand and so forth. And so a whole bunch of the mathematics and the formalisms there was borrowed with some adaptations from basically from chemistry and like statistical physics, and then was applied to microeconomic theory. Now, that doesn't mean that the economy is like a chemical reaction. It just means that the same formalism is used to model both of them. Another example would be how differential equations are used to model all sorts of things, sometimes even the same equation, from traffic flows to the macroeconomy, to electromagnetism and all sorts of other states, or like population dynamics. Differential equations are ubiquitous, but it doesn't mean the systems are related. It just means that there's mathematical principles that both of them exemplify in different ways. Now, that's all I would say about this, especially when you think about Hilbert space. Remember what Sean Carroll actually said about Hilbert space a little while back. He said that Hilbert space isn't like three-dimensional space that we walk around in. It's really just I think he said it was math speak for, like I can't remember exactly what he said, a set of outcomes or something like that. Hilbert space is really just a very abstract way of defining a set of possible outcomes, and you have like a vector in that space that says sort of what sort of superposition of possible outcomes you're at, if you want to crudely phrase it that way. The point there is that is a very abstract mathematical description. You can describe lots of things with such an abstract system. The more abstract you go, the more systems you could possibly apply it to, because it gets more powerful, right? The downside might be that it becomes harder to actually apply it to the system because you've got more parameters and it's harder to solve and things like that. But anyway, the fact that a very abstract mathematical framework is applicable outside of the original context in which it was developed doesn't really surprise me that much, and I don't think it should surprise anyone. And I don't think it should lead us to conclude anything about the quantum nature of the brain, and indeed, as many of the people working in this field themselves say. However, there's a further point to be made about this, because in this paper here, which I should say IP does not cite, but I'm citing it in reference to what IP is saying, this paper is discussing the application of these quantum cognition models to cognition, to various aspects of psychology. And for those who watched the follow-up stream after the debate, I talked about this there. So apologies for the duplication there, but I thought it should be included here. Now, what are they saying here? They're arguing that the use of quantum mechanics to aid in psychological models, starting by, we discussed the use of these models, starting sharply by contrasting the need of these models to use quantum mechanical non-locality instead of contextuality. We'll talk a bit more about contextuality in a moment, but non-locality is like the spooky action of distance that happens when you have two entangled particles, you collapse one of them and then the other one immediately collapses as well, or at least that seems that happens, even if they're very far apart. Now, that's important because what they're saying in this paper here is that contextuality in the form of quantum interference between like two waves, say, is the only relevant quantum feature used by these psychological models. Non-locality doesn't play a role. Now, since contextuality is also present in classical models, we propose that classical systems be used to reproduce the quantum models instead. Now, the basic idea is that all that these models use is interference, and that's a wave phenomenon. So as they say here, non-locality and contextuality are intimately related since the former requires the latter to happen in contexts that are changed at baseline. So, however, when taken by itself, contextuality is not a surprising phenomenon, but rather a common one. Whereas non-locality is still a disturbing and unusual feature of quantum systems, quantum mechanics. In our opinion, what is interesting about the works of people who've published in this quantum cognition field is not the use of quantum dynamics, but the implied contextuality of observables. Our claim is that they seem to show compelling evidence that interference, like interference between waves, may play an important role in cognitive processes, but this interference need not be of quantum origin. And they talk about how they present a sketch of a possible origin of these kind of interference effects. It could be that coupled oscillators, whose activity can propagate across the brain as a wave, may interfere with each other and thereby give rise to high-level interference of these patterns of neural activity, which would lead to interference effects and thereby what they call in contextuality. And this can be used to model various cognitive biases that we have, or at least what are called cognitive biases. Well, like if you ask question A and then question B, you might get a different answer to question B than if you just ask question B by itself. That could be like an interference effect. And that's an example of the sort of thing that these models are used for, to understand why is it that asking one question before you ask a second question makes a difference. Because if you just think, well, I just have two attitudes and I'll just report them when you ask me, then why does it make a difference how you ask them? But if there's some interference between the questioning, then that can be modeled by these processes. But the point of this paper is to show that, look, these models don't actually use all of the stuff that is relevant to quantum mechanics. It's just interference. And that's basically a wave phenomenon that can be understood in classical terms. So I think that's a very interesting paper there and shows that we should be very cautious in over-interpreting these quantum cognition models and thinking that there's more quantumness about it than there really is, where it's really just wave interference, which is actually a fairly common thing that happens. Waves are a very generic phenomenon that occur in many different contexts and don't have anything intrinsically to do with quantum mechanics. All right, get back to the video.
The intermental brain can be modeled like the quantum world. The brain is more likely to be quantum computing instead of classically computing.
Okay, so quantum cognition is this mathematical approach, and from Wikipedia, they
I don't actually want to talk too much about
superpositions. Not like physical objects or chemicals bouncing around inside our heads. Thus, the inner world of the mind, our thoughts, emotions, dreams, quality, etc., would be distinct from the physical world, like how Hilbert space is distinct from space-time. In other words, there is a
Okay, so this is more philosophy. Again, I'm focusing just on the science here. Now, he gets into some neuroscience, but I think, oh yeah, that's the same paper there. I think I don't want to get into the neuroscience today, but there is one more paper that I want to discuss here, which is one of the worst, well, the second worst. The worst one would be that one about the simulation, by the data scientist guy. But this comparison of the neuronal network to the cosmic web is pretty bad as well. So I did want to discuss this. What on earth is left? Okay, so I've skipped some mostly philosophy stuff.
Have recently published
here's another
where they
paper
point
here.
out that there are interesting similarities between neural networks and the cosmic web of galaxies. Recently, astrophysicist Franco Vazza and neurosurgeon Alberto Faletti wrote an article on the similarities between both. Is the apparent similarity just a human tendency to perceive meaningful patterns in random data? Remarkably enough, the answer seems to be no. Statistical analysis shows these systems do indeed present quantitative similarities. They note the similarities line up with information processing, power spectrum analysis, total neuron to total observable galaxies, and in many other ways. If idealism is true, then this is readily explainable.
Well, actually, I should
with the rest of the data we have presented. Both form the same physical structure, because both are emergent from an underlying mental reality. Under idealism, the brain is simply seen as the physical manifestation or second-person experience of a first-person conscious experience. And it fits with the idealist view that the whole universe would be structured in the same way, since it is also the emergent physical manifestation of mind. Thus,
all right, so IP is claiming that this paper provides evidence that there is some sort of structural similarity between matter distribution in the universe and neuron distribution in the brain, and that somehow this is explicable. This is more explicable under idealism than under materialism. Now, I think the philosophical, that's highly dubious. I have no idea why you would expect the brain to look like the cosmos if idealism was true, because they're just two different things that exist in God's mind. Like, why not trees or clouds or like anything else would not look the same? I don't know why you would connect those two. But again, I want to focus on the science here. So does this paper even show this? I think you know what the answer is, but let's have a look. Does the paper provide evidence that there's some similarity, structural similarity between neurons in the brain and like the cosmic web of galaxies? So I actually wonder if this study might be a joke. It is a real study published in like a real journal by real scientists. Pretty sure they're real scientists, right? Unlike the one about the physical world as virtual reality. But I just don't really get it. I don't know why this was done. There's no clear hypothesis here. Basically, they just say, well, some people have said that like the universe kind of looks like a brain, like the distribution of neurons in a brain, so maybe they're connected. I don't like, if I propose any investigation based on something like that as a graduate student, I'd just be laughed out of the office. Like, that's not a scientific hypothesis. So I don't really know why this was even done. I actually wonder if it might be some sort of joke or an inside. I actually have no idea, but anyway. So what are they actually looking at here? So they're looking at images of the cosmic web of galaxies. I don't actually know specifically where they came from, like this exact image. But they're looking at this, obviously imaged in a very particular way here. And then they're looking at two different images from two different micrographs of parts of a brain. So I assume it's a human brain. I don't know if they actually say that there. So cerebellum is one part of the brain that's kind of like at the back of the cortex, and then there's some tissue from the cortex itself. I don't know if it says where exactly, but anyway, and it's at different magnifications here. You can see. So that's what they're looking at here. And what they're doing is they're comparing the power spectrum. Remember, we talked about that from the cosmic micro background radiation. So it's a description of basically literally here they're just comparing the images. So it's how the density of pixels varies between the images, basically. That's what the power spectrum describes. Okay, and here's the different magnifications. Here's the cortex and cerebellum in the different colors, and then there's the cosmic web of dark matter and of baryons. I don't know if this image here is showing that. Oh, it's the dark matter. Okay, I was wondering why it was not sparser than that. So this is the dark matter. There's more dark matter than baryonic matter, so I guess that's why we're seeing more of it. So yeah, there's those two there. And this one on the right here takes out the 4 times and the 10 times, and we just see cerebellum and cortex at the 40 times, as well as dark matter and baryons, and then a few other systems that they've compared it to, like tree branches and clouds and so forth. Now, why did they only use 40 times slices? Well, the reason is because the other ones just didn't fit. As you can see, they're very different. It's only the 40 times ones that kind of fit, so the others have been ignored. So they've just cherry picked these slices here and ignored these ones. So already it's like, well, the cosmic web and the cortex kind of match if you zoom in at the right level. But there's a bit more to it than that, because these power spectral graphs here, they don't match to each other in any meaningful way. I think, did I maybe not put that quote in? Oh yeah, here it is. This is from the paper. It should be stressed that the power spectra are free to be slid horizontally in the plot, in the sense that the reference scale L related to k = 1 is decided a posteriori, which means arbitrarily. That's like science speak for we just decided. So basically, although these two lines are like on top of each other here, you could slide them arbitrarily along the horizontal axis, and it would be just as correct, right? So they're putting them on top of each other to emphasize that their shape is similar, but the position is arbitrary. So they've already picked the zoom level to make it fit. They've now picked the horizontal position to make it fit better. Notice also that this depends on the staining method used to stain the neurons, and that's fundamentally what I want to say here. They're comparing the pixel intensities of these two images. I'm not quite sure how this was produced. I think it's just looking at the amount of matter that's there, so that would be through cosmological observations and then building a model on the basis of it. But these images are constructed by staining the neurons in a particular way. I don't know what staining method was used here, but when you just look at neural tissue in a slide like this, if in a thin section, it's mostly transparent. You don't really see much of anything. You have to stain the neurons in order to see anything, and the stain that you use will affect what you see. So the stain that they've used here seems to be in the cerebellum. Like there's a bunch of cell bodies here by the look of it, but then there's, I don't really know what these tracts here are. Maybe they're white matter. This appears to be, I guess the neurons are probably just bigger here because the cell bodies are much larger here. You can see a few of those. I don't. These tracks are potentially axons or dendrites or something. It's a bit unclear. What you get when you get a slice here is you get a two-dimensional picture of a 3D web of cells. So it looks a bit chaotic there. But the point is, if you stain differently, you get a different image. And so it's entirely dependent on the staining method that they've used and the zoom level that they've used, as well as the type of neural tissue that they've picked. And so that's why I call this meaningless twaddle. It's just like we've compared an arbitrarily selected image of a particular staining of a particular part of the brain, and it kind of, if you squint, looks like a particular image of a particular part of the cosmic web at a particular zoom level. Kind of. Like, what is that supposed to tell us about anything? It's so silly. I don't understand why this would be expected under anything. I don't think there's any effect here. This is just like data mining a meaningless correlation between two images that have been constructed in ways. So I don't see how there's any scientific validity to that, which is why I say I wonder if it's actually a joke, because I don't see why any scientist would waste their time doing that. Anyway, so I think that was all I wanted to talk about from the first video there. Now I want to, so I don't know why I shared it again. Now I want to switch over to another video to talk a little bit about some of the other quantum studies before we finish out here. So this is from a different video, Quantum Physics Debunks Materialism version 2. Okay. And these are, so this is not arguing for the emergent space mind. This is more arguing for the fundamental role of consciousness in quantum mechanics. So there's a few papers here that I wanted to discuss. I think I've actually jumped a bit too far in the video, because the first one is, I'm not going to play the video all the way through because there's just a few studies that I wanted to pick out here. Okay, so the first one relates to the delayed choice quantum eraser experiment. Geez, where does he talk about this?
Demonstrated the same result. Problems. Just focus on.
Yeah, the Copenhagen interpretation is highly limited. That's fine. I know he talks about this here. Am I imagining it? I found the other ones here. Maybe he doesn't talk about it in this one. I thought he did. Bear with me a moment here.
Even atoms.
Oh, no. He does mention it here. Delayed choice quantum eraser.
Shows objectivity.
But does he not show the actual diagram of it? I thought that was in this paper. In this video, rather. I don't actually see the diagram that I'm looking for here. That's what he's showing here is the initial double slit experiment, which is fine. The electron would collapse one or the other. Oh, that's annoying. I thought it was in this video. All right. Well, I'll jump over to the next one that he does that is definitely here, because he talks about. I think this is. All right. Yeah, Leggett Inequality. That's what I wanted here. So let's start around here somewhere.
And proposed an inequality. If this inequality was shown to be false, then the local hidden variable theories would be falsified, and matter would be dependent on observation. This was put to experimental test in 1982 by Alan Aspect, and the results confirmed Bell's predictions. Bell's inequality was violated. This confirmed what quantum mechanics was telling us. Prior to measurement, objects have no defined properties or location. The act of an observer creates the existence of the physical objects and the properties they entail.
Who deserves to trust their intuition more than Einstein? And Einstein's intuition told him, like everybody's intuition tells them, that things are really there when you're not looking at them. Well, he was wrong, right? That intuition is incorrect.
To avoid this, many like John Bell proposed the existence of non-local hidden variables and the existence of Leggett's inequality. However, in 2007, they were also falsified, this time by Anton Zellinger and his team. Then in 2013, the last testable loophole was closed, showing there are no classes left of testable hidden variables. The collapse of the wave function and the existence of physical particles clearly must depend on the observer, not on some unknown hidden variables somewhere in nature.
So recent experiments led by a group at the University of Vienna, Austria, provide the most compelling evidence yet that there is no objective reality beyond what we observe. So it's really the observation that creates the reality. What they found is that Leggett's inequality is violated as well as Bell's. Even if you allow for instantaneous influences, quantum measurements do not fit with the idea of an objective reality. So as they say in the magazine, rather than passively observing it, we in fact create reality.
And then on top of this, the Kochen-Specker theorem.
Oh, we'll get back to the Kochen-Specker theorem. Yeah, look, I'm not even going to talk about Bell's inequalities because I'm trying to focus mostly on the papers that he specifically cites. I guess he did cite a few with respect to that, but I can't go through everything. Let's talk about Leggett's inequality because he does mention this in quite a few different videos. So you have to be careful when physicists are talking to a popular audience, they actually often misrepresent their own results, or at least represent them in ways that are philosophically dubious. But let's talk about Leggett's inequality. So what this result is often stated as showing is that, well, basically something like what IP was saying. There is no objective reality outside of the measurements we make, or like we somehow create the reality when we make measurements. Now, this I'm quite confident saying is not a correct interpretation, or at the very least, it's not the only interpretation. But I suspect that it's probably not even a cogent interpretation. But so, what does it actually say? Well, it's very complicated, so I'm not going to do it full justice. But I do want to discuss a few points here. And I think this is mostly taken from this paper here, Quantum versus Macrorealism. What does the Leggett inequality actually test? It's a very long paper, and I tried to understand it as best as I could. So I don't want to claim that I've perfectly got all of the details, but what they discuss here is that the Leggett inequality proves that you can't have you can't have both of these things. So let's talk about what that means. So Legg and Gugg begin their discussion by noting most physicists have a very non-quantum mechanical notion of reality at the macroscopic level. So this means, ordinary objects and observed and so forth, which makes two assumptions. Macroscopic realism, a macroscopic system with two or more macroscopically distinct states available to it, will at all times be in one of either of those two states. So like, typical example of this would be like Schrodinger's cat. It's either alive or it's dead. It's not both at the same time. And the second one is non-invasive measurability at the macroscopic level. That means it is possible in principle to determine the state of the system with arbitrarily small perturbation on its subsequent dynamics. So there's actually two claims that they're looking at here in the inequality: macroscopic realism and non-invasive measurability. So you can determine a macroscopic state to arbitrary precision without perturbing it. Now, Leggett and Gugg think that A1 implies A2. They argue, this is discussed further in the paper. But according to the paper, and I tend to agree with this, A1 does not imply A2. They're separate assumptions. And what follows from the inequality is you can't have both of these, right? But I'm not explaining that very well. You can't have both of these, okay? So that means you have to give up at least one of these. And often what it's described is in terms of you have to give up macroscopic realism. That is, you have to give up the idea that macroscopic objects are in a definitive state, not some sort of superposition of states, right? But actually, you can just give up various forms of non-invasive measurability. That is, it's not possible in principle to determine the state of a system to arbitrary precision, or with arbitrary small perturbation on subsequent dynamics. Now, that is something very different. That's a limit on measurability, not a limit on what actually exists. So let's have a look at another part of the paper, which I think explains this fairly well. Oops, sorry, clicked off that. Okay. In such a theory, so this is just talking about a particular understanding of the inequality, it is quite clear how a Leggett-Gugg inequality can be violated, / a measurement turn out surprisingly to be operationally disturbing, while yet the theory remains fully macro-realist. So that's the assumption one here. One might have demonstrated that a measurement is operationally non-disturbing for every operational eigenstate preparation that has been performed, without it being the case that it is operationally non-disturbing for every preparation that might arise. So the effect of the measurement could still be ontically invasive. It may shuffle the ontic states around. I'll explain how this fits together. I'm just going through the quotes here, and then we'll put it together. Blah, blah, blah. What allows the Leggett inequality to be violated is not the existence of ontic states which are not macro-definite. So again, that's referring to assumption one here. But the existence of novel probability distributions over the ontic states that are not given by mixtures of operational eigenstates. And to pull that together, we'll look at this last quote here, and I'll explain what this is saying. A crucial role is played, this is from the abstract, a crucial role is played in the argument by the assumption of non-invasive measurability. We show that this notion is ambiguous between the weaker notion of disturbance at the operational level, which is kind of like a macro level, and the very much stronger notion of invasiveness at the ontic level of properties of the system, which, as far as I can tell, they mean like at the underlying quantum level. Ontic non-invasiveness would be required to rule out macroscopic realism per se, but this property is not entailed by macroscopic realism. And its presence cannot be established in a model-independent way, which is their point here. It might be true, but it can't be established. So what does all this mean? As far as I can understand this, what it's saying is that these inequalities show, and the resulting experiments which demonstrate violation of the inequalities, that you can't have both of these things. But that doesn't mean you can't have macroscopic realism. It just means that at the underlying level, when you make a measurement, it must disturb the system to some extent, right? More than like an arbitrary small perturbation. But it doesn't mean that the system can't be in a macroscopic state and that your measurement must disturb the macroscopic state. So within any macroscopic object, there are many, many degrees of freedom. Like, you know, here's my hand, right? You can see my hand, right? Yeah. My hand doesn't appear to change if I just hold it here, even though there's actually atoms all over the place. And there could be an atom here that like moved over slightly to the left, or I could change two atoms around and like you wouldn't know the difference, right? These are internal degrees of freedom. There are different ways my hand can be without at the macroscopic level being different in any way that we can really tell. So the point there is that when I measure my hand, just by looking at it, say, or with some other device, I might be perturbing it at like an underlying kind of micro level, but I don't have to, at least according to some of these interpretations, this is what this paper is saying, that doesn't mean I'm perturbing it at a macro level, which would mean like changing it in a macroscopically visible way. So you can look at Schrodinger's cat. Well, I should be careful here because Schrodinger's cat is supposed to be in a superposition. But if I look at a cat, right, it doesn't mean that there's no state that it's in at a macro level. It may just mean that my looking at it, the photons bouncing off or being reflected off, does have some micro effect on the system, which is kind of, you would have thought anyway, right? But it doesn't have to change it macroscopically in some sort of detectable or significant way. That is effectively what this is saying when it's distinguishing between at an underlying ontic level here. Ontic non-evasiveness would be required to rule out macroscopic realism per se, but this property is not entailed by macroscopic realism, and it's a much stronger notion than disturbance at the operational level, which is like at a higher macro level. So basically, this requires that there is invasiveness at the micro level. The violations of this equality imply, as far as I understand it, that there must be that any measurements must basically disturb the system at a kind of a micro level, change it into a different state, which is what it's saying here. But it doesn't mean that it has to disturb it into a different state at the operational level, which is like at the macro level that we see. And therefore, it doesn't follow that you can't have macroscopic realism. So the interpretation of this result is, as far as I can tell, again, not an expert in quantum foundations, but as far as I can tell, grossly misrepresented in a lot, even by Leggett and Garg, I think, misrepresent this. And that's what this whole paper is discussing, really, that they themselves misrepresent their result here, and others in popularizations as well. The crude way to say this is that it just seems to be that when you observe a quantum system, it affects the quantum system, but not necessarily at a macro level, just at a quantum level. It doesn't mean that we're creating a reality whenever we perform, whenever we're performing a measurement. That would be macroscopic. That would be the first principle there of macroscopic realism, but it hasn't been shown to be violated. It's those two together that you can't have, macroscopic realism and non-invasive measurability. But non-invasive measurability only needs to be violated at a micro level, not necessarily at a macro level. So we can still have macroscopic objects that exist as they are without and are not affected in a significant way by observation, just at a micro level by observation, which isn't, at least to my mind, that surprising that it's affected in some way. So that's my best attempt to understand the relevance of this theorem here. Let's now jump back to the video. Hang on. I've opened up another tab now. I've got to choose the right one. Yeah, this one. But yeah, you will sometimes still hear physicists talk about the Leggett inequality, because I mean, IP quotes some examples, and I've seen others, that it does imply macroscopic realism is false. But I think that is a misrepresentation, misinterpretation, or misapplication of the theorem there.
Was experimentally confirmed in 2011. The philosophical implications also support the notion physical reality is not there without an observer, as Anton Zellinger explains.
The Kochen-Specker Theorem talks about properties of one system only. So we know that we cannot assume, to put it precisely, we know that it is wrong to assume that the features of a system which we observe in the measurement exist prior to the measurement. Not always, I mean in certain cases. So in a sense, what we perceive as reality now depends on our earlier decision what to measure, which is a very, very deep message about the nature of reality and about our role in the universe. We are not just passive observers.
In other words, the Kochen-Specker Theorem confirms the notion of reality is dependent on observation. You can't separate observers from reality, like the idea of watching nature play out on a stage. Our actions now very much determine the results, especially the collapse of the wave function and the existence of particles in their physical form. This only correlates with the conclusions of this study, which shows objectivity, determinism, and independence combined are incompatible with any theory about the universe, and not only with quantum mechanics, but with classical approaches as well. In other words, you can't have a universe that is objective, deterministic, and also independent from observers, as we once thought. All the data has confirmed this through multiple experiments, that reality is dependent on...
All right, I'm going to stop it there. I just wanted to see how far it goes. So we talked about the Leggett Inequality. Now let's talk about the Kochen-Specker Theorem. Again, there are some other papers that he references here, but I don't claim to be going through everything. There are a few main ones that I wanted to focus on, and this is one of the others here. So let's talk about Kochen-Specker Theorem. We're nearly there. The only other one I wanted to look at is delayed choice quantum eraser, but I can't seem to find the video that I wanted. Anyway, so let's talk about Kochen-Specker Theorem. That's the one that the physicists were just talking about there. Again, the popularization of this is often, I think, a misrepresentation, although I don't think it's quite as bad. I'm not going to go through exactly what the Kochen-Specker Theorem actually is or says per se, but we're just going to look at this paper here, which relates to quantum contextuality. So you may recall that I mentioned this a few times in the past, the notion of quantum contextuality. I mentioned it in the case of quantum cognition theories. What is this idea of quantum contextuality? It's a very difficult concept to discuss, I think, and this paper is actually talking about this, that even physicists often sort of get this wrong, and that they're confusing epistemic contextuality with a formal understanding of contextuality as exposed by the Kochen-Specker theorem. So, but let me sort of skip to the four main points here that they discuss. Again, this is a fairly difficult paper, but I hope I've sort of got the main gist of it. So what is the point of the Kochen-Specker theorem? The Kochen-Specker theorem is a sort of a proof of an aspect of quantum contextuality, which basically means that all aspects of a system cannot be given definite values simultaneously. That's a crude description of it. Now, this is sometimes described as meaning that what exists depends on what you measure, but I don't think that's a very good way to put it. As this paper says, so the Kochen-Specker theorem makes exclusive reference to quantum formalism. So that means that the notion of contextuality makes reference only to quantum formalism. Now, why is that relevant? Point 3 here. The Kochen-Specker theorem has nothing to do with actually performed experiments. There is no need of actual measurements for the Kochen-Specker theorem to stand. It's a purely formal result. It's not empirically testable. You can't, as it says here, quantum mechanics does not allow you to measure simultaneously different properties of the same system at the same time, which is in fact what the Kochen-Specker theorem is kind of referring to. So the Kochen-Specker theorem is a formal result. It doesn't have anything to do with measurements. And so although you can describe it in terms of measurements, but that's misleading because it's not about the measurements at all. It's about what is defined within a quantum system. And what it says is that the states that, or the values in a quantum system that can be given definitive values, let me rephrase that. You can't give every possible set of measurements that you can make. You could imagine assigning values to them, like, okay, this number is 1, this is 2, and this is 3, and then I'll take a different set of measurements, and maybe I'll measure like 4, 5, and 6, and so on. Now, you can imagine writing all those down and saying, here are all the different combinations, and here are all the corresponding values of the measurements that I've made. Depending on the thing that I measure, here are the values that I'll see, and depending on this thing, I'll see these values. What quantum contextuality is saying, and the Kochen-Specker theorem it relates to, is that you can't define all of those numbers at the same time in a single quantum system, because they're inconsistent. It proves that they're, at least in some quantum systems, as was said in the interview, not in every case, but in some quantum systems, you won't be able to define all of them at the same time. So this is a little bit like I'm not saying this is literally an example of this because I'm not actually sure, but it's a little bit like the Heisenberg uncertainty principle, where you have space and momentum, position and momentum. You can't define both of them at the same time. The more precisely you define position, the less precisely you have to define momentum. again, not exactly the same here because you need to talk about more than two variables, but it's a sort of similar idea that you can't define the values of all variables at the same time because they kind of affect each other. To prove that, you have to go through kind of these like 3x3 tables, and it gets a bit formal. So I didn't really want to go through that here. So it might seem a bit vague, but it's actually fairly easy to show this. Like the proofs aren't hard. It's just a formal result. You can't define all of the properties of a quantum system with respect to certain types of measurements at the same time because of basically interference between different aspects of the quantum system. Like it just doesn't make sense to define them all at the same time. Quantum systems sort of have interference properties internally that classical systems just don't have. So that's why it's called contextuality. It's contextual. The way you interact with a quantum system will determine whether you get this set of measurements or this other one. But that doesn't depend on you actually making the measurements. The making the measurements is just a way of seeing that, right? So that's why, as it says here, it's not something that the Kochen-Specker theorem is not something that's testable. It's just a result that follows from the formalism of quantum mechanics. So what does this mean? It means that you can't use the Kochen-Specker theorem to say that we like create reality in some way, because it's nothing to do with the actual physical making of the measurements. It's about the formalism. The formalism doesn't allow you to define everything at the same time that you might have thought you could define. There'll be inconsistent sets of variables, and the measurement that you actually make will, of course, like that depends on which version of it you see. Kind of like if you look at a complex object from different viewpoints, you'll see it in different ways. But that doesn't mean that you've created the object. Like just because I'm looking at it in a different way and therefore see different aspects of it, that doesn't mean I've created the thing. It just means that you look at it in different ways, you see different things. Now, it's a bit more than that because according to the quantum contextuality, there's no actual like true reality of the quantum state. There's just different, I guess there's different ways to look at it is one way to say it. And you can't define them all at the same time. Anyway, so that's a very sort of crude level, and I don't want to say that I've exactly explained it there, but it's too difficult to try to articulate that without going through the maths formally. But basically, you can't define all the aspects of a quantum system that you might have thought you could, and the way you could in a classical system. It just doesn't work that way. But it doesn't have any it doesn't directly follow that we somehow like create the reality. It means that when we take measurements, we do have to decide what aspect of the system we're going to measure. And when we take that measurement, we'll get the corresponding measurement. But we didn't create anything. We chose to observe the existing quantum system in a specific way. So we got a specific type of result. That's all this is saying. All right. Oops, I keep clicking on the wrong button there. Let's go back to the video and let's see if I can talk a bit about delayed choice quantum eraser. Let me just see what he...
Observers. Whether it is independent from observer. You can't have a universe that is objective, deterministic, and also independent from observers, as we once thought.
Yeah, so this needs to be qualified. So I didn't actually look at the paper that he's directly quoting from here. But again, you have to be very careful when you're looking at these labels because these are often operationalized in very, very specific ways. Just like we were talking about in the case of the Leggett inequality, right? Where we talked about macroscopic realism and the other principle of, what was it again? How was it phrased? A non-invasive measurability. It turns out that there's different conceptions of non-invasive measurability, and we had to be very cautious about which one we were talking about. So whenever the claims are made like this, you have to ask, like, how are these being defined in the specific theorem? And I'm not sure about the exact theorem, the exact paper this was talking about, but the point there would be that these would be defined in a specific way. And I very much doubt that this paper or any of the others, because every example that I've looked at, you're like, it doesn't show that the world is actually not objective. What it will usually mean is there are different, like it's contextual, right? The way you interact with a system affects how you observe the nature of that system. In that sense, it's contextual, but it doesn't mean it's not objective. It still exists independent of humans. It's just the way we interact with it there's different ways of interacting with it, and you'll sort of measure different things. That's generally what these sort of contextual results are saying. Not that there's no reality outside measurement.
All the data has confirmed this through multiple experiments, that reality is dependent on observers. Whether it is the interaction-free experiments, Cheshire Cat experiments, delayed choice quantum eraser experiments.
It is. Okay, so maybe that was earlier in the video, but I couldn't actually find this diagram anywhere. Maybe it was a different video where he goes through the detail of this one. But anyway, so I have talked about this in a previous video in a lot more detail. So I'll just go through this briefly now and finish this out here. So because this has gone on a little longer than I'd hoped. So, but IP uses the delayed choice quantum eraser experiments as he is doing here to argue that a conscious observer is involved in collapsing the wave function and affects, therefore, what exists in reality. But this is a misinterpretation. Or I guess you can interpret the delayed choice quantum eraser experiment that way, but you're certainly not required to. And I'd say that's a very minority interpretation of what's happening there. So let's have a look at what the delayed choice quantum eraser experiment is actually saying here. Okay, so here's a setup. I'm just seeing how much I've got on this. All right. So the delayed choice quantum eraser experiment is a variation on the double slit experiment. In the double slit experiment, you have a light source, you shine it through two slits that are near each other but not like separated, and the light diffracts. It diffracts through the slits and then disperses, creating two waves, which then interfere with each other and produce a diffraction pattern. An interference pattern on the far wall. I think he showed I've gone off it now. And so the interference pattern will look something like this on the far wall there. Now, the funny thing about the double slit experiment is that you see an interference pattern even if you only shoot one photon at a time. So the idea is you shoot a photon, it's emitted as a particle, it passes through presumably one of the two slits because it's a particle, right? It's localized, and then it travels through the space and hits the the detection apparatus on the far side and is observed at one specific point. Okay, so far so good. But then you shoot lots and lots of these photons, one at a time, and over time you build up the pattern of where they fall on the far side, and what you actually see is an interference pattern. So there was only ever one photon in the apparatus at a time. So how did you get an interference pattern? Answer: the photon must have existed as a wave as it propagated through the space between the emitter and the detector, passed through both slits and interfered with itself. So the strangeness here is that the photon, or you can do it with electrons or whatever you want, but I'll just call it photons. The photon was emitted as a particle and absorbed as a particle, but propagated as a wave. So this is an instance of wave-particle duality. It's kind of cool, right? That's quantum mechanics. Now, that's the standard double slit experiment. How does the delayed choice quantum eraser work? So it turns out that if I stick a detector at one of the slits, or like both of the slits, I guess, to see which of the two slits my photon goes through, then I lose the interference pattern. Basically because I've collapsed the wave function at the slit, and the photon behaves as a particle. It only goes through one slit, therefore does not interfere with itself because it's not a wave anymore, and then hits one particular position on the far side of the wall. So you don't get an interference pattern. So if you have knowledge of which slit the photon went through, then you lose the interference pattern. Now, the delayed choice quantum eraser experiment takes that up a notch by basically having an experimental setup which allows you to basically determine which slit the particle went through after the particle has already gone through the slits, which is why it's sometimes described as like erasing the past, because it's like, well, it's already passed through one of them, but then you like erase that knowledge and then you can get back an interference pattern. But that's the idea, but it's really misleading, right? Because there's no erasure going on. It's not changing the past or anything of the sort. That's just a popularization. Let's see what's actually happening here. Now, this is different to the diagram that IP used, but I think it's actually a slightly clearer one, but it's the same setup here. So you've got a source of photons that shoots through the double slit apparatus here. And then I forget what BBO stands for exactly, but this is a device that produces a copy of whichever of the photon that hits it. And produces them in an entangled state, which means they're both describable by the same quantum system. So there's a particular setup that allows them to do this. The details don't matter for our purposes. So basically, it just makes a copy, if you like, of the photon, but entangled, so it's the same quantum system. So that's why we've got two sort of rays passing here, corresponding to the two different photons that have passed through. Okay, no, sorry, I said that right. One of the photons goes this way and one goes this way. So one's called the signal photon and one's called the idler photon. The two colors actually represent which slit the initial photon went through, not which direction it goes in. So there's the signal and the idler. They're both entangled with each other, so they're in a sense like the same, but they travel in different directions because of the way the device is set up. So the signal photon is just passes through a lens and then hits the D0 detector here, so that's fine. What happens to the idler photon? Well, the idler photon has a longer path, which is called idler because it doesn't travel slower, but it takes longer to get to the detectors, so it's detected afterwards. Now, what happens to it? Well, it passes through a prism, which deflects it a little bit, and then it passes through some what's BS stand for? It's a lens that allows the someone will in the comments will remember what this stands for, but it's a lens that 50% of the time allows the photon to pass through, and 50% of the time reflects it off into this direction. So it splits it. It splits the light into two, but probabilistically. So half the time it goes this way, half the time it goes this way. Likewise for this one here. So look at this idle photon here. If it hits this and then is deflected into D3, that's the only way you can get a photon at D3. So it must have come from this slit here. So we've got which path information. That's what this is called. We know which path this photon went through. It passed through this slit and then was bounced and went to here. Therefore, we know which of the slits the photon went through, which means we also know which slit this one went through because they came from the same slit. You'll see that if you follow the blue path here, this one also comes from that slit. So they're both the same. They both came through the same slit. It's just they were split after the fact. So if we measure a detection at D3, we know which slit this photon traveled through, which means that we won't observe a diffraction pattern there or an interference pattern there. Likewise, if we observe the photon at D4, that just means it came from the other slit. So if we observe photons appearing there, we won't see an interference pattern there. But what about D1 and D2? Well, in that case, notice that there's an extra step here because here the idler passes through this lens here. It's not bounced out, but it goes through, and then it hits this mirror. And likewise, this one hits this mirror, and then they pass through another one of these sort of 50-50 devices, which bounces the. Notice it does this in both directions. It bounces the photons so that they're now on the same path. So notice that at D1 and D2, because of this extra bouncing pathway here, when I measure a detection here, I don't know which slit the photon came from because it could be either of them. It could be the blue or it could be the green. I don't know because they've been superimposed back onto each other essentially. So if I have a measurement at D1, I don't know which slit the photon came from, and therefore I do not have which path information. Likewise at D2. So you will not expect to see an interference pattern as a result of measurements from D1 or D2 because sorry, I said that the wrong way. You would expect to see an interference pattern because here you don't know which slit that it went through, which is equivalent to sort of saying it went through both slits, right? Whereas in these ones, you do know which slit it went through, and then it must have gone through only one of the slits. Just like if you were just to stick a measuring device at one of the slits, and if you do that, then it passes through that slit, you don't get an interference pattern. But if you remove that, then it passes through both, you do get an interference pattern. Okay, that's the setup here. So a beam splitter, yes, sorry, thank you. That's what the BS stands for, the beam splitter. It's really quite simple. I don't know why I forgot that. It splits the beam, yeah, not complicated. Okay, so that's the basic setup. Now, I need to explain a little bit more here about what you actually observe here, because that's what's shown on the side here. Now, when you actually run this experiment, right, I mean, there's subtle differences of how you can run it, but just imagine that these beam splitters are randomized. So sometimes you get a detection at D3, sometimes D1, and so on. And on each trial, you can't predict. But you will make observations and you'll pick up these detections, and likewise at D0. What will you actually see in terms of the patterns here? Well, you will see these interference patterns at D1 and D2. So that's what this shows here. D1 and D2 will show these interference patterns. They will actually be offset with each other because there's a phase difference there. I don't know if I exerted the part that talks about that, but basically these beam splitters here, or maybe it's the mirror actually, or is it both? Well, one of these two beam splitters are mirrors, or possibly both of them. I actually can't remember now, but they introduce a phase difference, which don't worry too much about what that is, but just notice that these are offset. The peaks are offset with the troughs here so that they sort of like they fit into each other, like a cos and a sine wave, right? They're offset from each other. That's introduced by the experimental apparatus, and there's no way of avoiding that. Any way you do this, you're going to get this offset here. Now, that's important, and we'll come back to that in a moment. But the point is you do get interference patterns at D1 and at D2, as shown here. You do not get interference patterns at D3 and D4 because you'd have which path information, so it only came through one slit, and therefore no interference because it can't interfere with itself. If it's like acting as a particle going through just one slit. So that's all fine. But what do you observe at D0? Well, the answer is, now I actually want to show this here. Surely I put this in here. Well, the point I'm making is oh yeah, here it is. So this is excerpted from the paper, but I've just put it in text here. So this guy found is not emphasizing the analysis of others, is that there never appears an interference pattern at D0 without conditioning on whether we choose which path information to be available or erased. So if you just look at D0, you never observe an interference pattern. And this is in one of his videos, I'm not sure which one, but IP gets this wrong because he says there'll be an interference pattern at D0. At least it seems that it's ambiguous exactly what he means, but I think he's saying you observe an interference pattern at D0, but you don't, not by itself. So when I'm seeing photons appearing at D0, you never see an interference pattern. You just get a big clump here. It's like smeared out. You only get an interference pattern at D0 if you condition on whether photons have arrived at D3 at D1 or D2. Now, what does that mean? It means that if a photon arrives at D1, that means that I should also expect the corresponding signal photon to be, because they're entangled, right? They're the same quantum system, essentially. So I expect the signal photon to be correlated, so to basically appear at a similar location, a corresponding location on this detector compared to this detector, or likewise for D2. But that only happens for the photons that I observe at D1. It doesn't happen for those that I observe at D2, that they're shifted, right? So basically what you see on D0 is the superposition of D1 and D2 on top of each other. Notice that if you put those on top of each other, you're going to get something like this, which is not an interference pattern. This top one here is not an interference pattern. That's just the two bands corresponding to the two slits. These ones are the interference patterns. If you put them on top of each other, you get this. So at D0, if you just look at D0, you just see this, right? There's no interference pattern there. You only get the interference pattern if you just say, okay, let's take only those trials where D1 that hit on D1 or D2 for that matter. Where do I see the photons appearing on D0 when I only consider D1? And then you'll see an interference pattern. Likewise, if you just take D2. But if you put them on top of each other, you never see both at the same time. So that's what this point is making here. You only see an interference pattern on D1 when you condition on which path information on whether you're looking at D1 or D2. And that's also not just which it's D1 or D2, but also it doesn't happen if you condition on D3 or D4, because in those cases you have which path information, so there will be no interference pattern in those cases. Now, why does all of this matter, right? All of this matters because what IP and others say is that it's whether you get an interference pattern at these different particularly D0 depends on whether like a conscious observer and when a conscious observer decides to like make a measurement and then they can collapse the wave function in a particular way. But that is not implied in any way by this experiment, nor is any backwards causation or anything of the sort, because you never get an interference pattern at D0 unless you condition on what's happened elsewhere, D1 and D2. So as it says here, each subcase shows an interference pattern. So the D1 or the D2, but not both of them together. There is no way to avoid the phase difference in the interference fringe, since any device acts symmetrically on both paths. So whatever you do on one affects the other, and so the phase difference will always continue. So that's what I said here. D1 and D2 alone will result in interference pattern, but because of the phase shift, the two patterns offset and show there's no interference. This means that you can never tell by looking at because D1 is D0 is observed before you observe any of these, because the idler photon's path is longer. That's why it's called a delayed choice, because this happens after this is observed. But you can't work out what's going to happen by looking at D0, because there's no interference pattern there. You can only work it out after you've made the measurement here, and then say, conditioning on having made the measurement here, whichever one it was, wherever you eventually observed it, because it could be at any of these, conditioning on that, then I see an interference pattern. But that's only after you've taken the measurements. So there's no sort of backwards causation thing here. If this photon if the signal photon is detected first, then you can just say, well, look, whatever happens to the signal photon, that causes whatever happens to the idler photon. There's no backwards causation necessary there, because you never observe the interference pattern until afterwards. When you go back and look at your correlations, you see, oh yeah, there's a correlation between D1 and D0. You don't observe that on D1 alone. So it's not like you can tell where this idler will end up just by looking at D0. It never works like that. So there's no sense in which a conscious agent like decides where it can end up. So let me emphasize this point with a few highlights here. In the standard explanation, if the detection of the idler photon happens before the detection of the signal photon, the detectors D1 to D4 determine what state the wave function collapses to. So if you make this detection first, this determines where this one will end up. But if you make this detection first, this one will determine when this one ends up. So there's no backwards causation. Whichever one you make first, it determines what happens to the other one. Let's see. Yeah, so that's what it just said there. The view that the detected position of the single photon collapses a wave function of the idler photon to trigger one of the detectors is just as accurate. However, in this case, the observation of where the photon lands on the screen does not tell which state the overall wave function has collapsed to. For the reason that I just said, if you just see where this ends up, it doesn't tell you what the collapse is because you only see an interference pattern after you've looked at what happens here and make the correlations. As soon as the signal photon gets entangled, the photon states lose their coherence. So as soon as you make a measurement, there's decoherence. But there's no backwards causation because you can never like work out what's going to happen here before it happens or something, or say that where it ended up here was caused by what happened afterwards at which of these, because you never observe the interference pattern there. That's the fundamental problem of interpreting it that way. What this tells us is that no matter how the idler photon gets manipulated, or when it's looked at, or when a conscious observer sees it or doesn't see it, the probability distribution on D0 is a clump pattern. But when we condition on the outcome of the detectors, they either give which bunch of information or don't. We find the correlations as expected, or no correlations in the case of D0, where it's just a clump pattern. Sorry, D3 or D4, when it will just give a clump pattern. So these will not give interference, these ones will. So hopefully that was at least a little bit clear. Yeah, so in the instance that I described, D0, the path to D0 is shorter in the physical setup, which is why that's the other one's called the idler, because it's behind. But you can change that if you wanted to. You could observe them in any order, and it doesn't matter whether a conscious observer sees it or not. That's completely irrelevant. Observation means detection by a physical apparatus. I mean, you could stick your eyeball there if you wanted to, although that would probably just screw up the whole process. But anyway. So consciousness has, as far as we can tell, nothing to do with it. I mean, you can postulate that if you like. I'm not saying it rules it out, but there's no evidence to favor that. And the delayed choice quantum arrays, it doesn't say anything about conscious agents, and it doesn't say anything about backwards causation either. All it says is that whichever one you measure first, that measurement collapses the whole system and then causes or affects where the other one will end up being detected. And you only see an interference pattern on D0 when you condition on the other set of measurements. So you need the whole set of measurements to see interference at D0 anyway. You can't use that to like say, well, I measured at one of the other measurements, but that retroactively determined where the photon fell in D0, which I could tell that it would happen. It doesn't work like that. So that's the fundamental problem. And that's why in some of his videos, not necessarily in the one we just looked at, but in some of the videos, I think IP misinterprets it by saying that there's an interference pattern at D0, which is produced only because a conscious observer saw it or something like that. That's a misinterpretation. All right, so those are all the papers that I want to talk about today. There's obviously other papers that he cites, but that IP cites in different videos, but I was never intending to go through those. I've already gone a bit longer than I wanted. So the point that I wanted to make here, let's just summarize a bit. There are quite a lot of papers and principles that IP cites, inspiring philosophy cites, largely in behalf of evidence of like the emergence of space and time and gravity from quantum effects, and also in favor of particular interpretations of quantum mechanics, generally like a consciousness causes collapse. There's also something he cites on quantum cognition as evidence to link the cognition or the mind to quantum mechanics. As far as I can tell, in all of the papers, IP does not correctly represent the science. Now, I should be clear here because some people have criticized my title. When I say he misrepresents the science, I don't mean that he's doing this knowingly or deliberately. Misrepresents just means misrepresents in an incorrect or misleading way. It doesn't mean that it's intentional. I don't mean to imply that. I also don't mean to imply that he gets literally everything wrong. I try to be very specific in the aspects of which it was, I think, incorrect, either in directly what he said or in terms of the implications or the way it was presented. There is a lot of interesting science in what IP does talk about, and some of it's fine, but there's a lot of aspects of it that are not fine, that's, I think, are overtly just incorrect or represented in a misleading way or subject to different interpretations. So hopefully I made some of that clear today. I'll put up in a bit, I'll put up the links to the papers that I've talked about so you can have a look at those for yourselves. Thanks for listening. Hopefully this was interesting, and I'll talk to you guys next time. See ya.